Hello there, and welcome back to the Science Sleepy Minds, that gentle corner of the internet where the vastness of existence becomes your bedtime lullaby. Tonight, you find yourself drifting somewhere extraordinary. Picture this. You're floating 1.5 million kilometers from Earth, suspended at a gravitational sweet spot where the Sun, our planet, and the Moon perform an eternal balancing act. Before you unfolds the largest mirror ever launched into space, 18 hexagonal segments of beryllium coated in gold, so thin you could measure it in atoms. The James Webb Space Telescope hangs here in the cosmic dark, its sunshield the size of a tennis court, blocking the warmth of our star so that its instruments can chill to temperatures colder than anything naturally occurring on Earth. You probably will not survive this vacuum, not without a spacecraft anyway, but your imagination needs no oxygen tank. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment telling me where you're listening from and what time it is where you rest your head tonight. Are you in Tokyo watching the sunrise? Perhaps in Vancouver as the rain taps your window? Maybe Sao Paulo, where the city never quite sleeps? Wherever you are, you belong here. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The story of the James Webb Space Telescope begins not in the silence of space, but in the noisy corridors of bureaucracy, budget meetings, and bold scientific ambition. Back in 1996, astronomers started dreaming of a successor to Hubble, a telescope that would not merely extend our vision, but fundamentally transform it. They called it the Next Generation Space Telescope, a name so generic it could have belonged to a vacuum cleaner. Eventually it was renamed after James E. Webb, the NASA administrator who shepherded the Apollo program through its most turbulent years. Historians still argue whether naming scientific instruments after administrators rather than scientists sets the right precedent, but the telescope itself cares nothing for human debates. It simply watches. Construction took over 2 decades. Engineers faced problems that had never existed before because no one had ever attempted anything quite like this. The primary mirror needed to be larger than any rocket fairing could accommodate, so they designed it to fold like cosmic origami, 18 separate segments that would unfurl once in space and align themselves with nanometer precision. Each segment is about the size of a coffee table, and together they form a light collecting area more than 6 times greater than Hubble's mirror. The gold coating, by the way, amounts to roughly 48 grams total, about the mass of a golf ball. That gilded surface is not decorative vanity. Gold reflects infrared light with exceptional efficiency, and infrared is Webb's native language. You see, Hubble taught us to see the universe in visible light, the same wavelengths your eyes detect when you glance at a sunset or read these words on a screen. But visible light has limitations. Dust clouds absorb it, scatter it, hide entire stellar nurseries behind veils of cosmic soot. More importantly, the oldest light in the universe has been stretched beyond recognition. When photons left the first galaxies over 13 billion years ago, they were energetic ultraviolet rays. But the expansion of space itself has tugged at their wavelengths, reddening them, pushing them into the infrared spectrum where Hubble is essentially blind. Webb was built to see what Hubble could not, the universe's earliest chapters, written in heat rather than colour. Launch day arrived on December 25, 2021. A European Ariane 5 rocket carried the telescope from French Guiana into the pre-dawn sky, a Christmas gift to every curious soul who ever stared upward and wondered. The journey to Lagrange Point 2, that gravitational parking spot behind Earth relative to the Sun, took about a month. During that transit, mission controllers held their breath through 344 single-point failures mechanisms that had to work perfectly or the mission would end. The sunshield deployed its 5 delicate layers. The secondary mirror swung into position. The primary mirror segments unfolded, locked, and began the painstaking process of alignment. Each step succeeded. By late January 2022, Webb had arrived at its forever home, a place so far from Earth that astronauts could never visit for repairs. Unlike Hubble, which was famously fixed by spacewalking heroes, Webb must function flawlessly or not at all. The engineers built their confidence into every joint and actuator, and so far, that confidence has been rewarded. Cooling came next. The instruments needed to reach temperatures around 40 Kelvin, colder than minus 230 degrees Celsius, so cold that the telescope's own heat would not blind it to faint infrared whispers from across the cosmos. One instrument, the mid-infrared instrument known as MIRI, required even more extreme chilling, 7 Kelvin, achievable only through an innovative cryocooler that essentially refrigerates the detector to temperatures colder than interstellar space itself. By mid-2022, Webb's eyes were open, its instruments calibrated, and scientists around the world waited for the first images with the kind of anticipation usually reserved for births and football finals. What arrived exceeded every expectation. On July 12, 2022, NASA released the first batch of full-colour images, and the internet collectively gasped. Galaxies spiraled in impossible detail. Nebulae glowed with colours that seemed painted by some celestial artist who'd grown bored with subtlety. And there, in the flagship image known as Webb's first deep field, thousands upon thousands of galaxies crowded into a frame representing a sliver of sky so small you could cover it with a grain of sand held at arm's length. Each smudge of light was an island universe containing billions of stars, and behind them lurked even more galaxies, their light bent and magnified by the gravitational pull of a foreground cluster. The scale was incomprehensible, and yet there it was, rendered in pixels, downloadable to your phone, shareable with your grandmother. Tonight you and I will wander through what Webb has revealed, from the birth of the first stars to the atmospheres of distant worlds, from the paradox of galaxies too mature for their age to the lingering mystery of why the universe seems to be expanding at 2 different speeds depending on how you measure it. We will encounter black holes that grew too fast, dark matter that shapes everything yet touches nothing, and nurseries where stars are born inside cocoons of gas and dust. Along the way, we will grapple with the true scale of existence, a scale so vast that even astronomers sometimes pause mid-calculation and mutter something unprintable. But for now, rest your eyes on that golden mirror in your mind. Feel its chill, sense its patience. Webb does not rush. It gathers photons one by one, ancient travellers that left their sources when Earth did not yet exist, when the sun was merely a possibility written in collapsing hydrogen. Those photons have been journeying toward this moment longer than multicellular life has graced our planet, and now they end their voyage on a detector no larger than a postage stamp. From there, the signal travels back to Earth, decoded by computers, interpreted by humans, and eventually whispered to you through speakers or earbuds as you settle deeper into your pillow. The universe has been waiting to tell you its story. Webb is merely the translator. So breathe slowly. Let the hum of your fan or the silence of your room become the ambient noise of deep space. We have 20 sections to explore, 20 steps deeper into the cosmic dark. By the end, the universe will feel both infinitely larger and strangely more intimate, because understanding scale does not diminish wonder, it multiplies it. You are made of atoms forged in stars that exploded before our solar system, condensed from their debris. Tonight you trace that lineage backward, photon by photon, toward the beginning of everything, and if you happen to fall asleep along the way, that is perfectly fine. The universe will still be here when you wake, and so will the next section, waiting patiently like starlight that has travelled 13 billion years just to greet your closed eyelids. Let us continue. You find yourself now inside the concept of infrared light, a form of radiation your body knows intimately, even if your eyes cannot perceive it. Every warm object emits infrared. Your skin, your coffee mug, the laptop gently heating your thighs. When you stand near a campfire and feel warmth on your face before the visible flames lick close enough to illuminate you, that sensation is infrared radiation crossing the gap between combustion and nerve endings. The universe is no different. It glows with heat signatures that visible light telescopes cannot detect, and Webb was designed specifically to read those thermal whispers. To understand why this matters, picture the electromagnetic spectrum as an impossibly long piano keyboard. Visible light occupies barely a single octave somewhere near the middle, the narrow band your retinas evolved to interpret because it happens to pass through Earth's atmosphere and bounce off the objects your ancestors needed to see. Predators, prey, potential mates. But the cosmos plays far more notes than that cramped octave. Radio waves rumble at the base end, their wavelengths stretching meters or even kilometers. Gamma rays scream at the treble extreme, wavelengths so short they can slip between atoms. Infrared sits just below visible red, a mellow baritone section your eyes ignore but your skin acknowledges every time you feel sunshine through a window. Here is the crucial trick the universe plays. When light travels across cosmological distances, it does not arrive unchanged. Space itself is expanding, and as it stretches, so do the wavelengths of photons traversing it. Imagine drawing a wave on a rubber band and then pulling the band longer. The wave's peaks spread apart, its frequency drops, and what started as a tight blue vibration becomes a lazy red undulation. This phenomenon is called redshift, and it means that the oldest light in the universe, photons emitted by the first stars and galaxies, has been stretched so dramatically that it no longer qualifies as visible light at all. It has shifted into the infrared, invisible to instruments like Hubble, perfectly visible to Webb. Scientists sometimes call this ancient infrared glow the cosmic fossil record. Just as paleontologists dig through rock strata to find bones of creatures long extinct, astronomers peer through layers of red-shifted light to witness epochs when the universe was young, hot, and utterly alien to anything we know today. Webb is essentially an archaeological instrument, sifting through electromagnetic sediment to recover relics from the first few 100 million years after the Big Bang. No visible light telescope could ever accomplish this because the evidence simply does not exist in that wavelength range. The universe has hidden its baby photos in infrared, and Webb arrived with the correct decoder. There is a charming irony here. Humans built fires and forged metal, and invented electricity largely by learning to manipulate heat, yet we spent most of scientific history blind to the thermal radiation surrounding us. William Herschel discovered infrared in 1800 by accident, while measuring the temperature of different colours of sunlight split through a prism. He noticed that his thermometer registered heat even beyond the red end of the spectrum, in a region where no visible colour existed. He had stumbled upon an entire hidden domain, and he did not even have a proper name for it. Scholars still argue whether Herschel fully grasped the significance of his discovery, or whether he considered it a curious footnote. Either way, that footnote eventually grew into modern infrared astronomy, culminating in a $6 billion telescope parked at Lagrange Point 2. Webb's infrared sensitivity comes from its detectors, sophisticated arrays of mercury-cadmium telluride and arsenic-doped silicon designed to register photons with wavelengths between 0.6 and 28 microns. To give you a sense of scale, a human hair is roughly 70 microns thick, so we're talking about wavelengths smaller than a single strand divided into portions. These detectors must be kept extraordinarily cold because any warmth generates infrared noise, like trying to hear a whisper while standing next to a jet engine. That tennis court sunshield exists precisely to block solar radiation and allow the telescope's cold side to drop to cryogenic temperatures. Even so, the MIRI instrument requires additional mechanical cooling to reach 7 Kelvin, a temperature at which molecular motion nearly ceases and the detector becomes exquisitely sensitive to faint cosmic heat. What does Webb actually see with this capability? Imagine you're staring at a dense cloud of dust and gas, a stellar nursery where new suns are coalescing from gravitational collapse. In visible light, the cloud appears as a dark silhouette against background stars, an opaque curtain hiding the drama within. Switch to infrared, and suddenly the curtain becomes translucent. Dust particles scatter visible photons but allow longer infrared wavelengths to pass relatively unimpeded. Webb can peer inside the nursery, observe protostars gathering mass, watch accretion disks spinning around infant suns, and detect the jets of material that newborn stars fling into surrounding space. It is the difference between standing outside a theatre and actually sitting in the front row. The same principle applies to distant galaxies. Many of the earliest cosmic structures formed inside hazes of primordial gas that absorbed and scattered visible light. Hubble could glimpse only the brightest beacons through that fog, like headlights dimly visible through dense mist. Webb's infrared vision cuts through the haze, revealing galaxies that Hubble never registered, objects so faint and so red-shifted that they might as well have been invisible. In the first year of operation alone, Webb detected candidate galaxies from redshifts above 10, meaning their light left when the universe was less than 500 million years old. Some candidates suggest redshifts of 12, 13, even higher, epochs so early that theorists assumed galaxies had not yet finished forming. Webb disagreed, and theorists are still adjusting their spreadsheets. There is a delightful quirk worth mentioning. Because infrared wavelengths correspond to heat, Webb can also study objects within our own solar system by detecting their thermal emissions. It has imaged Jupiter's auroras, mapped the temperature variations on Saturn's moon Titan, and observed asteroids as they tumble through the void. These observations occur at the opposite end of the distance scale from the early universe, yet they rely on the same fundamental capability, seeing the cosmos in heat rather than colour. Webb is versatile that way, equally comfortable examining a comet a few 100 million kilometres away, and a galaxy 13 billion light-years distant. Of course, infrared astronomy is not without challenges. Earth's atmosphere absorbs most infrared radiation, which is why ground-based infrared observatories must perch on high mountaintops in dry climates, or send balloons to the edge of space. Even then, atmospheric interference limits sensitivity. Webb sidesteps this problem entirely by operating in the vacuum of space, beyond any atmospheric absorption, free to collect infrared photons without terrestrial contamination. Lagrange point 2 offers additional advantages: constant solar illumination for power, a stable thermal environment, and an unobstructed view of the sky unblocked by Earth or Moon. The location was chosen with the precision of a chess grandmaster anticipating moves several turns ahead. You might wonder why it took so long to launch an infrared space telescope of this caliber. After all, Hubble flew in 1990, and infrared technology existed for decades before that. The answer lies partly in engineering complexity, folding mirrors, cryogenic coolers, sun shields, and partly in funding politics. Webb's budget ballooned from an initial estimate of around $1 billion to nearly $10 billion by launch, a cost overrun so severe that Congress nearly cancelled the project multiple times. Scientists fought for it, arguing that the discoveries would justify every penny. So far, the discoveries have exceeded even optimistic projections, and no one in the astronomical community is complaining about the price tag anymore. Value, it turns out, depends on what you value, and knowledge about the universe's origins ranks high on many lists. Tonight, as you drift through these explanations, let infrared become more than a technical term. Think of it as a secret language the universe speaks when visible light falls silent. Webb has learned that language, and now it translates for the rest of us. The messages arriving at its detectors are older than Earth, older than the Sun, older than most of the atoms in your body. They are whispers from the cosmic dawn, stretched into warmth by billions of years of expansion, and finally captured by gold-coated beryllium mirrors orbiting a small blue planet that did not exist when the whispers began. Sleep with that thought, and let the infrared glow of your own body remind you that you too are part of this thermal conversation. The first deep field image released by Webb landed on human screens like a gentle earthquake, the kind that does not topple buildings but shifts foundations invisibly. You've likely seen it by now, perhaps scrolling past on social media, perhaps lingering as a desktop wallpaper, perhaps glimpsed in a news article and dismissed as another pretty space photo. But linger with me here, because what that image represents deserves more than a casual glance. To create it, Webb stared at a tiny patch of sky near the southern constellation Volans for approximately 12.5 hours. The target was a galaxy cluster called SMACS 0723, a massive congregation of galaxies whose combined gravity bends space-time like a funnel. That bending acts as a cosmic magnifying glass, amplifying and distorting the light of far more distant galaxies behind the cluster. Astronomers call this gravitational lensing, and we'll explore it more deeply in a later section, but for now simply understand that Webb was using the cluster as a natural telescope, boosting its already formidable reach. What emerged from that exposure was a riot of light. Thousands of galaxies crowd the frame, some appearing as elegant spirals, others as fuzzy ellipses, still others smeared into arcs and streaks by the lensing effect. The variety is staggering. You see galaxies edge on, their dust lanes dark slashes across bright cores. You see galaxies face on, spiral arms trailing like cream stirred into coffee. You see galaxies colliding in slow gravitational dances that will take hundreds of millions of years to resolve. And behind them all, fainter still, you see the faint red smudges of galaxies so distant their light has been travelling since the universe was less than 1 billion years old. Here is the unsettling fact that kept astronomers awake in the weeks following the image's release. The patch of sky Webb observed is astonishingly small. Hold a grain of sand at arm's length, and the area it covers against the night sky is roughly equivalent to the deep field's extent. Now consider that similar density of galaxies likely fills every comparable patch across the entire celestial sphere. Extrapolate that density to the full sky, and you arrive at estimates suggesting the observable universe contains somewhere between 200 billion and 2 trillion galaxies. The uncertainty in that range is itself humbling. We're not even sure within an order of magnitude how many galaxies exist. Webb's image did not answer that question definitively, but it provided data points that future surveys will refine. What struck scientists most forcefully was not the quantity, but the quality of the faint distant objects. Several of the reddest smudges in the deep field turned out to be candidate galaxies at extreme redshifts, meaning their light originated in epochs far earlier than many models predicted for robust galaxy formation. Initial analyses suggested some of these objects might date from just 300 million years after the Big Bang, a cosmic blink so brief that theorists assumed only the most primitive structures could exist. Yet there they were, glowing faintly in Webb's infrared detectors, hinting at stellar populations and organised structures where chaos was supposed to reign. The debate over these objects continues, and we'll wade deeper into that controversy shortly, but the deep field ignited it with undeniable evidence. Historians of astronomy will someday compare this image to the Hubble Deep Field of 1995, which similarly transformed our understanding of cosmic scale. Back then, Hubble stared at a seemingly empty patch of sky in Ursa Major for 10 consecutive days, revealing galaxies where ground-based telescopes saw nothing. That image became iconic, reproduced in textbooks and planetarium shows for decades. Webb's deep field accomplishes something analogous, but at higher resolution and longer wavelengths, pushing the frontier several 100 million years closer to the Big Bang. If Hubble showed us the universe's teenage years, Webb is revealing its infancy, and perhaps even its birth cries. A quirky footnote from the image's release involves the public reaction. Social media exploded with comparisons, memes, and philosophical musings within minutes of the official announcement. Some users joked that the image resembled glitter scattered on black velvet, a cosmic craft project gone magnificently awry. Others noted that the brightest objects in the frame, the stars of our own Milky Way, are marked by distinctive diffraction spikes, those six-pointed star shapes caused by Webb's hexagonal mirror segments and secondary mirror supports. Those spikes became almost a visual signature, appearing in subsequent Webb images and sparking debates among astrophotographers about whether they enhance or distract from the scientific content. Astronomers mostly shrugged. The spikes are optical artifacts, not targets, and the real treasures lie in those faint background smudges. What does the deep field tell us about scale? Consider this. The light from the most distant galaxies in that image has been travelling for over 13 billion years. When that light began its journey, the universe was a fraction of its current age. Stars were just beginning to forge heavier elements, and the concept of a planet like Earth was still billions of years in the future. Those photons crossed voids where nothing existed, passed through expanding space that stretched their wavelengths, dodged the gravitational pulls of countless intervening masses, and finally landed on a detector built by a species that did not exist when the journey started. Every pixel in the deep field represents an almost miraculous survival, a message in a bottle thrown across cosmic oceans and somehow arriving intact. Scale also manifests in what you do not see. The deep field shows only a sliver of the observable universe, and the observable universe is itself a limited bubble defined by the finite speed of light and the age of the cosmos. Beyond that bubble, space presumably continues, filled with galaxies and structures we will never observe because their light has not had time to reach us. Some cosmologists speculate that the total universe may be vastly larger than the observable portion, perhaps infinitely so. Webb cannot peer beyond the cosmic horizon, but it pushes our vision closer to that edge than any previous instrument, and in doing so, it reminds us how much remains hidden. There is a peculiar emotional quality to staring at deep field images late at night. The mind resists comprehension, bouncing off the numbers like a tennis ball off a concrete wall. 2 trillion galaxies, each with hundreds of billions of stars, many of those stars hosting planets. The arithmetic collapses into abstraction. Yet the image itself is concrete, a photograph as real as any snapshot from your phone. The disconnect between emotional grasp and intellectual acknowledgement creates a kind of cognitive vertigo, a dizziness that some philosophers call the sublime. Edmund Burke wrote about it in the 18th century, describing the mixture of terror and awe inspired by vast or powerful natural phenomena. He did not have access to Webb's deep field, but he would have recognized the sensation. Tonight, let that vertigo settle gently rather than unsettle. The universe's scale does not diminish you, it contextualizes you. You're a pattern of matter that became aware of the pattern, a brief arrangement of atoms capable of contemplating arrangements billions of light years away. That capacity is itself remarkable, a quirk of evolution on a rocky planet orbiting an ordinary star in one of those 2 trillion galaxies. Webb's deep field is not a reminder of insignificance, but an invitation to significance. It says, look, here is what exists, and here are you, able to look. Few things in the cosmos can claim that privilege. So rest your gaze on the imagined glitter of distant galaxies. Let them blur into abstraction as your eyelids grow heavy. The deep field will remain, frozen in data archives, waiting for future generations to study with even more powerful instruments. For now, it has done its job. It has shown us the neighbourhood, and the neighbourhood turns out to be unimaginably vast, unimaginably ancient, and unimaginably beautiful. Breathe slowly. The next section will bring us closer to those impossibly early galaxies, the ones that should not exist but stubbornly do. For now, let the image settle like sediment in still water. You're about to encounter a cosmic embarrassment, the kind of surprise that makes theorists wince and observers grin. When Webb pointed its infrared gaze at the distant universe, it found galaxies that had no business being there. Massive, mature, structurally organized galaxies existing at times when the cosmos was supposedly too young for such sophistication. Imagine arriving at a nursery and finding a few toddlers already holding doctoral degrees. The universe, it seems, did its homework faster than anyone expected. The standard cosmological model, known affectionately as lambda CDM, provides a remarkably successful framework for understanding how the universe evolved from a hot, dense state to the complex web of galaxies we observe today. According to this model, the first stars ignited around 100 to 200 million years after the Big Bang, coalescing from primordial hydrogen and helium in regions where dark matter's gravity had begun to gather gas. These early stars were likely massive and short-lived, burning through their nuclear fuel in mere millions of years before exploding as supernovae. Gradually, over hundreds of millions of years, small protogalaxies merged into larger structures, building up the kinds of grand spiral and elliptical galaxies we see in the nearby universe. The process was supposed to be slow, hierarchical, bottom-up, small things combining into big things over vast stretches of time. Webb's observations suggest the universe had other plans. Within the first year of science operations, astronomers identified candidate galaxies at redshifts above 10, corresponding to epochs roughly 400 million years after the Big Bang. Some candidates pushed even higher, toward redshifts of 12 or 13, meaning their light departed when the universe was barely 300 million years old. By itself, finding galaxies at these redshifts was not shocking. Theorists expected to see faint, small, irregular clumps of early star formation. What shocked everyone was the apparent mass and luminosity of these objects. Several candidates appear to contain stellar populations rivaling or exceeding the mass of the present-day Milky Way, compressed into a cosmic eye blink when such accumulation should have been impossible. The technical term for this predicament is the impossibly early galaxy problem, though some astronomers prefer the more cautious label, tension with expectations. The tension arises because standard models struggle to explain how so much stellar mass assembled so quickly. Stars need time to form from collapsing gas clouds, and the gas itself needs time to cool and condense within dark matter halos. The entire supply chain of galaxy formation has speed limits, and Webb's galaxies seem to have violated those limits like a sports car on an empty highway at 3 in the morning. Several explanations have been proposed, none yet confirmed. One possibility involves the efficiency of star formation in the early universe. Perhaps the first gas clouds converted matter into stars more rapidly than later generations, driven by conditions that no longer exist. higher cosmic densities, different chemical compositions, fewer disruptive influences like stellar winds and supernovae. If star formation efficiency was elevated by factors of 2 or 3 compared to modern galaxies, the mass accumulation problem becomes less severe, though still uncomfortable. Another possibility concerns the initial mass function of early stars. If the first stellar population skewed heavily toward massive luminous stars, the observed brightness of early galaxies might overestimate their total stellar mass. Essentially, we could be fooled by a few exceptionally bright stars masquerading as a much larger population. This explanation requires fine-tuning the assumptions astronomers use to convert light into mass, a process fraught with uncertainties even under the best circumstances. A more radical possibility invokes modifications to cosmological models themselves. Some theorists have explored whether dark matter behaves differently in the early universe, perhaps clumping more efficiently or interacting in ways not captured by the standard cold dark matter paradigm. Others have suggested tweaks to the timeline of cosmic reionization, the epoch when ultraviolet radiation from the first stars reionized the neutral hydrogen that filled space after the cosmic microwave background was emitted. If reionization occurred earlier or differently than assumed, galaxy formation timelines might shift accordingly. Historians of science will recognize this pattern. Whenever observations outpace theory, the scientific community responds with a mix of excitement and discomfort. Excitement, because anomalies are where discoveries hide. Discomfort, because anomalies threaten comfortable certainties and demand hard intellectual work. The early galaxy problem exemplifies this dynamic. Nobody is panicking. Lambda CDM remains extraordinarily successful at explaining large-scale structure, the cosmic microwave background, the distribution of galaxies across billions of light years. But the edges of the model, where predictions meet the earliest epochs, are fraying under Webb's scrutiny. One particularly intriguing candidate galaxy, designated JADAS GSZ 13-0, has drawn intense attention. Spectroscopic follow-up confirmed its redshift at approximately 13.2, placing its light emission around 320 million years after the Big Bang. The galaxy appears compact, with a stellar mass estimated in the tens of millions of solar masses, substantial but not wildly inconsistent with accelerated early formation scenarios. Other candidates remain less certain, their redshifts inferred from photometric colours rather than spectroscopic confirmation. The distinction matters because photometric redshifts can be fooled by dusty foreground galaxies mimicking the appearance of highly redshifted objects. Astronomers are working through the candidate lists, obtaining spectra where possible, refining estimates, and gradually separating genuine high redshift objects from interlopers. There is a delightful irony in all this. Webb was designed in part to find the first galaxies, to witness cosmic dawn and illuminate the processes that built structure in the young universe. The telescope has succeeded beyond expectations. Too far beyond, one might say, revealing a dawn more crowded and developed than models predicted. Success has become its own puzzle, and the puzzle is driving new research, new simulations, new theoretical frameworks. Science, at its best, works exactly this way. Observations challenge assumptions, assumptions evolve, and understanding deepens even when certainty wavers. What does this mean for you, drifting towards sleep with visions of impossibly early galaxies in your mind? It means the universe is stranger than we knew, which is always good news for curiosity. It means the story of cosmic evolution is not yet written, despite decades of confident diagrams in textbooks. And it means that Webb's mission is only beginning, each new observation a potential revision to the narrative we tell ourselves about how everything came to be. The telescope will continue gathering data for years, perhaps decades, accumulating evidence that future generations will interpret with tools and theories we cannot yet imagine. For now, let the impossibly early galaxies shimmer in your imagination like premature fireflies, glowing before the season should allow. Their existence is a mystery wrapped in infrared photons, and mysteries are the universe's way of keeping us humble. Sleep with that humility and dream of galaxies assembling in the cosmic dark, racing against clocks that theorists thought they understood. Tomorrow, the astronomers will return to their spreadsheets, their simulations, their arguments. Tonight, the mystery simply is. You wade now into the deepest waters of the impossibly early galaxy controversy, where the currents of theory and observation swirl in turbulent eddies. The term cosmic dawn refers to the era when the first stars ignited and the first galaxies coalesced, ending the cosmic dark ages that followed the release of the cosmic microwave background. Webb has not merely glimpsed cosmic dawn, it has photographed a sunrise more brilliant and complex than anyone anticipated, and the implications ripple through astrophysics like stones dropped into a still pond. The standard timeline of the early universe proceeds as follows. Around 380,000 years after the Big Bang, the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms, an event called recombination. Before this moment, the universe was opaque, a seething plasma that scattered light like fog scattering headlights. Recombination cleared the fog, releasing the cosmic microwave background, the oldest light we can observe, a snapshot of the universe as a nearly uniform sea of hydrogen with faint density ripples. Those ripples, amplified by gravity over hundreds of millions of years, grew into the first stars and galaxies. The Dark Ages intervened between recombination and the first starlight, a period lasting perhaps 100 to 200 million years, during which the universe contained matter but no luminous sources. Neutral hydrogen filled space, absorbing any photons that might have been emitted. Then, gradually, pockets of gas dense enough to collapse under gravity formed the first stars, objects theoretically dubbed Population 3 stars, a designation indicating primordial composition, essentially pure hydrogen and helium with negligible heavier elements. These stars were likely massive, perhaps hundreds of times the mass of the Sun, burning hot and brief before exploding as supernovae that seeded the cosmos with the first heavy elements. Webb's observations have complicated this neat sequence. If galaxies with substantial stellar masses existed by 300 or 400 million years after the Big Bang, the window for Population 3 stars shrinks dramatically. There simply is not enough time for a leisurely progression from first star to first galaxy. Either star formation began earlier than assumed, or it proceeded faster, or the definition of first galaxy needs revision. Scholars still argue whether the brightest early Webb candidates represent genuinely massive galaxies, or smaller objects whose light is magnified by gravitational lensing or boosted by unusually luminous stellar populations. One intriguing hypothesis involves active galactic nuclei, the brilliant cores powered by supermassive black holes, accreting matter at prodigious rates. If some of Webb's early sources harbour nascent black holes rather than purely stellar populations, their luminosities might mislead mass estimates. A black hole accreting gas can outshine an entire galaxy of stars while containing a tiny fraction of the mass. Disentangling stellar light from black hole light requires careful spectroscopic analysis, and astronomers are only beginning to obtain the necessary data. We will explore the supermassive black hole problem in a later section, but for now note that the cosmic dawn puzzle may involve multiple overlapping mysteries. Another hypothesis concerns the role of feedback in early galaxies. In the modern universe, stellar winds, supernovae and black hole jets blow gas out of galaxies, regulating star formation and preventing runaway growth. These feedback mechanisms take time to establish, however. in the first few 100 million years, before many supernovae had occurred, gas might have converted into stars with unusual efficiency, building stellar mass rapidly before feedback kicked in. Simulations exploring this scenario can produce early galaxies consistent with Webb's observations, though the required assumptions remain speculative. The cosmic dawn problem also intersects with rionization, the process by which ultraviolet radiation from early stars and black holes stripped electrons from neutral hydrogen atoms, making the universe transparent again to certain wavelengths. Observations of distant quasars and the cosmic microwave background suggest reionization completed by around 1 billion years after the Big Bang, but the timing of its onset remains uncertain. If Webb's early galaxies produced enough ionizing radiation, they might have begun reionization earlier than expected, altering the chronology in subtle but measurable ways. Future observations of the neutral hydrogen fraction at high redshifts will test this possibility. There is a human dimension to this scientific ferment worth acknowledging. Careers are built on models, and when models face challenges, emotions run high alongside equations. Some senior astronomers, having spent decades refining lambda CDM, approach Webb's anomalies with cautious skepticism, demanding extraordinary evidence before accepting extraordinary revisions. Younger researchers, perhaps less invested in existing frameworks, embrace the anomalies as opportunities, publishing papers proposing novel mechanisms or alternative cosmologies. The dynamic is healthy, even when debates grow heated. Science progresses through productive disagreement, and the early galaxy problem has generated plenty of material for productive disagreement. One particularly spirited debate concerns the reliability of photometric redshift estimates. Measuring a galaxy's redshift spectroscopically by identifying emission or absorption lines at known rest wavelengths and observing their shifted positions provides high confidence. Photometric estimates, based on the colours of a galaxy across multiple filters, are faster and can be applied to fainter objects but carry larger uncertainties. Several of the highest redshift candidates announced in Webb's first year relied on photometric estimates, and subsequent spectroscopic follow-up has revised some redshifts downward, demoting a few impossibly early galaxies to merely early status. The overall picture of surprisingly mature early structure remains, but individual claims should be evaluated with appropriate caution. What emerges from this swirl of data and debate is a picture of cosmic dawn as a more dynamic, more rapid, more complex epoch than textbooks described 5 years ago. The universe did not ease gently into galaxy formation. It sprinted, assembling structures with an urgency that challenges our understanding of the underlying physics. Whether this urgency reflects exotic new processes or merely our previous underestimation of conventional processes remains to be determined. Either way, the cosmos has revealed itself to be a faster builder than we gave it credit for. As you drift through these ideas, let them settle without demanding immediate resolution. Mysteries are not defects in knowledge, but features of ongoing inquiry. Webb has handed astronomers a glorious puzzle, and solving it will take years, perhaps decades. The tools required, more spectroscopy, better simulations, possibly new theoretical frameworks, are being developed even as you listen. In the meantime, the impossibly early galaxies shine in archival data, patient monuments to a cosmos that refuses to conform neatly to human expectations. They ask in their silent ancient light, "Did you think you had figured us out?" The honest answer, whispered back across billions of light years, is, "Not yet, but we are trying." You float now into the realm of redshift, that curious phenomenon where light changes colour simply by travelling through expanding space. To understand the scale of the universe that Webb has revealed, you must first grasp how astronomers measure cosmic distances, and redshift is the most powerful ruler in their toolkit. It sounds technical, but stay with me. The concept is simpler than it appears, and it unlocks profound truths about the nature of reality. Light travels at a constant speed, roughly 300,000 kilometers per second in a vacuum. Nothing in the universe can move faster through space, though space itself plays by different rules. Since the Big Bang, the fabric of space has been stretching, carrying galaxies apart like raisins in rising bread dough. This stretching does not violate cosmic speed limits, because the galaxies are not moving through space. Space itself is expanding, dragging galaxies along for the ride. And crucially, the expansion stretches the wavelengths of light travelling through it. Consider a photon emitted by a distant star billions of years ago. As it journeys toward us, the space it traverses expands, tugging at the photon's wavelength like fingers pulling taffy. Blue light becomes green, green becomes yellow, yellow becomes red, and red eventually slides into infrared and beyond. The degree of this stretching, expressed as a number called redshift, indicates how much the universe has expanded since the photon departed. A redshift of 1 means the universe has doubled in size during the photon's journey. A redshift of 10 means it has expanded 11-fold. Webb's most distant targets show redshift above 10, implying their light has been stretched by factors exceeding 11 times its original wavelength. Redshift also translates into look-back time. The duration photons have been travelling from source to observer. Because light speed is finite, observing distant objects is equivalent to looking into the past. When you see a galaxy at redshift 10, you see it as it existed when the universe was roughly 500 million years old. At redshift 13, you glimpse an epoch merely 300 million years after the Big Bang. Webb does not possess a time machine, but redshift converts its images into snapshots of cosmic history, each wavelength encoding a different moment in the universe's biography. The physics behind redshift is elegant. General relativity describes space not as an inert stage, but as a dynamic participant in cosmic events. Mass curves space, and cosmic expansion stretches it. Photons riding through this stretching fabric experience wavelength changes proportional to the expansion factor. This is not a Doppler shift in the classical sense. Galaxies are not flying away from us through static space like cars racing down a highway. Instead, the highway itself is lengthening, and the wavelength of light stretches with it. The distinction is subtle but important, especially when discussing objects receding faster than light. Yes, faster than light. Beyond a certain distance, the accumulated expansion rate exceeds light speed, meaning photons emitted from those regions will never reach us. They are beyond the cosmic horizon, forever outside the observable universe. Measuring redshift requires spectroscopy, the analysis of light broken into its component wavelengths. Atoms and molecules emit and absorb light at characteristic wavelength determined by quantum mechanics. Hydrogen, for example, emits a distinctive pattern of lines at specific wavelengths in the ultraviolet and visible spectrum. When astronomers observe a distant galaxy and identify hydrogen emission lines shifted into the infrared, they can calculate the redshift precisely. Webb's spectrographs excel at this task, capturing infrared spectra with unprecedented sensitivity and resolution, pinning down redshifts for objects that Hubble could not even detect. Here is a quirky historical footnote. The concept of redshift predates the discovery of cosmic expansion. In 1912, Vesto Slipher measured spectral shifts in spiral nebulae, as galaxies were then called, and noticed most appeared redshifted, moving away from us. He did not interpret this as universal expansion. The prevailing assumption was that the universe was static and eternal. It took Edwin Hubble's 1929 correlation of redshift with distance to establish that the universe was expanding, a conclusion that shocked even Albert Einstein, who had famously inserted a cosmological constant into his equations to prevent expansion. Einstein later called this his greatest blunder, though modern cosmology has resurrected the cosmological constant in the form of dark energy. Historians still argue whether Einstein's blunder was a blunder at all or merely premature insight. Webb's redshift measurements have sharpened our view of cosmic expansion by providing more accurate distance estimates. The telescope observes Cepheid variable stars and type Ia supernovae in distant galaxies, calibrating the cosmic distance ladder with reduced uncertainties. These calibrations matter because they feed into calculations of the Hubble constant, the number describing how fast the universe is expanding. We will explore the controversy surrounding this constant shortly, but understand that redshift precision is central to the debate. Webb's infrared eye pierces dust that obscures Cepheids in visible light, revealing stellar pulsations previously hidden and tightening the error bars that plague distance measurements. What does redshift feel like, if such a question even makes sense? Perhaps it resembles the way a train whistle drops in pitch as the train recedes, though the analogy is imperfect because expansion involves space itself, not motion through space. Or perhaps it resembles the way colours fade when viewed through tinted glass, though redshift is more systematic, shifting the entire spectrum uniformly. Ultimately, redshift is alien to everyday experience, a phenomenon observable only across cosmic distances where expansion accumulates to measurable degrees. Your walk to the kitchen does not redshift. The universe is not expanding fast enough to notice across a few meters. But across billions of light years, the effect becomes dramatic, transforming ultraviolet starlight into invisible infrared, hiding the ancient cosmos from optical telescopes and revealing it only to instruments like Webb. Tonight, as you drift through these ideas, let redshift become a kind of cosmic poetry. Every photon arriving from the distant universe carries a record of the expansion it endured, a wavelength diary written in stretched light. Webb reads those diaries and translates them into images, spectra, and data tables. Behind every number is a story of space stretching, of time passing, of light journeying longer than planets have existed. The universe communicates through redshift, and Webb has learned to listen. Close your eyes and imagine the spectrum of a distant galaxy. Bright emission lines shifted far into the red. Signatures of hydrogen and oxygen and nitrogen displaced by billions of years of cosmic growth. That displacement is not loss, it is information, preserved across unfathomable distances, waiting for a golden mirror to catch it. You've arrived at one of modern cosmology's most persistent headaches, a discrepancy so stubborn that astronomers have given it a nickname, the Hubble tension. The tension refers to a disagreement between two methods of measuring how fast the universe is expanding, a disagreement that Webb has not resolved but has confirmed with uncomfortable clarity. Understanding this tension requires patience, but the payoff is a glimpse into physics that may lie beyond current theory. The expansion rate of the universe is quantified by the Hubble constant, denoted h0, measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so the constant describes how much faster a galaxy recedes for every additional megaparsec of distance. If h0 equals 70, a galaxy 1 megaparsec away recedes at 70 kilometers per second, a galaxy 2 megaparsecs away at 140 kilometers per second, and so on. The value of h0 determines the age of the universe, the distance to remote objects, and the geometry of space-time. Getting it right matters enormously. Two primary methods exist for measuring h0, and they yield stubbornly different answers. The first method uses the cosmic microwave background, the afterglow of the Big Bang, observed with exquisite precision by satellites like the European Space Agency's Planck mission. By analysing the patterns of temperature fluctuations in this ancient light and feeding them into the lambda CDM cosmological model, physicists can extrapolate what H0 should be today. Planck's result hovers around 67 km per second per megaparsec, with uncertainties so small they should leave little room for doubt. This second method builds a distance ladder from nearby stars to distant galaxies, using objects whose intrinsic brightness is known, standard candles, to calibrate cosmic distances. Cepheid variable stars, whose pulsation periods correlate with luminosity, provide the first rung. Type Ia supernovae, thermonuclear explosions of white dwarf stars, provide a brighter rung visible across greater distances. By combining these measurements, astronomers construct a direct ladder from the solar neighbourhood to galaxies hundreds of megaparsecs away, deriving H0 without invoking cosmological models. This method, championed by teams using Hubble and now Webb, consistently yields values around 73 km per second per megaparsec. The discrepancy between 67 and 73 might seem small, but given the precision of modern measurements, it amounts to a roughly 5 sigma disagreement, statistical jargon meaning there is less than 1 chance in a million that the difference is due to random error. Either one method has an undetected systematic flaw, or the lambda CDM model is incomplete, missing some ingredient that causes the universe to expand faster than predicted. Webb entered this debate with the precision of a forensic auditor. Its infrared vision allowed astronomers to observe Cepheid variable stars in host galaxies of type E supernovae with unprecedented clarity, reducing confusion from crowded stellar fields and dusty environments. Early results, published in 2023 and refined since, confirm the distance ladder measurement of H0 near 73, tightening error bars and ruling out some proposed sources of systematic error. If anything, Webb made the tension worse by demonstrating that the discrepancy is not an artifact of Hubble's limitations. The problem is real. What could explain the tension? Several possibilities circulate in the literature. One involves early dark energy, a hypothetical form of energy that boosted expansion shortly after the Big Bang, then dissipated before the present era. If early dark energy existed, it would alter the inferred value of H0 from the cosmic microwave background, potentially reconciling the two methods. Another possibility involves modifications to dark matter, perhaps allowing it to interact with radiation in ways that affect the sound waves imprinted on the microwave background. Still another involves changes to the expansion rate in the very late universe, perhaps driven by evolving dark energy or local density variations that bias the distance ladder calibration. Historians of cosmology note that tensions between measurements have arisen before and often heralded new physics. The discrepancy between predicted and observed perihelion precession of Mercury, for instance, pointed to the inadequacy of Newtonian gravity and eventually led to general relativity. The unexpected faintness of distant Type Ia supernovae in the 1990s revealed the accelerating expansion of the universe and the existence of dark energy. The Hubble tension may represent a similar crack in the edifice, a hint of something beyond lambda CDM waiting to be discovered. Or the tension may resolve mundanely. Unidentified systematics in either method could shift the results. The distance ladder in particular involves multiple rungs, each introducing potential errors. If the Cepheid calibration is slightly biased, the entire ladder shifts. If supernova luminosities vary in unaccounted ways, distances are misjudged. Webb's observations have addressed some of these concerns, but cannot eliminate all possible systematics. Similarly, the Planck analysis depends on assumptions embedded in lambda CDM. If the model is wrong in subtle ways, the inferred H0 inherits those errors. There is a certain dramatic irony in the situation. The Hubble constant is named for Edwin Hubble, who first quantified cosmic expansion nearly a century ago. His initial estimate, around 500 kilometers per second per megaparsec, was wildly wrong due to calibration errors in the distance ladder of his era. Subsequent decades saw zero estimates fluctuate, sometimes contentiously, as astronomers refined their techniques. The current tension echoes that history, reminding us that measuring the universe's expansion rate has never been straightforward. For you, drifting through these concepts in the quiet dark, the Hubble tension offers a curious comfort. Even with the most advanced telescopes ever built, even with decades of refined theory and meticulous observation, the universe retains surprises. We do not have all the answers. The cosmos is not a closed book, but an ongoing mystery, each chapter raising new questions. Webb has provided the clearest evidence yet that the tension is genuine, not a measurement fluke. Whatever resolution emerges, new physics, subtle systematics, or something entirely unforeseen, it will deepen our understanding of cosmic evolution. Sleep on that uncertainty. Let it soften rather than disturb. Certainty is comfortable but static. Uncertainty is uncomfortable but generative. The Hubble tension is generative, driving theorists to propose new models, observers to seek new data, and instrument builders to plan future telescopes capable of even sharper measurements. In the grand arc of scientific progress, tensions like this are not failures but invitations. Webb has extended the invitation, and the astronomy community has RSVP'd with enthusiasm. Tomorrow, or next year, or next decade, the tension may dissolve into clarity. Tonight, it simply hums quietly in the background, a cosmic puzzle awaiting its solution. You turn now to the stars that serve as cosmic mile markers, the Cepheid variables, and their role in Webb's assault on the Hubble tension. These pulsating giants have guided astronomers for over a century, and Webb has refined their message with infrared precision, transforming blurry data into sharp calibrations. Cepheid variable stars breathe, not biologically of course, but in a rhythmic expansion and contraction that causes their brightness to rise and fall over periods ranging from days to weeks. This pulsation is not random. It obeys a tight relationship between period and luminosity discovered by Henrietta Swan-Leavitt in 1912. Longer period Cepheids are intrinsically brighter than shorter period ones. Measure the period, infer the luminosity, compare that to the observed brightness, and you have a distance. It sounds simple, and in principle it is, but decades of work have been spent refining calibrations, accounting for metallicity, correcting for dust extinction, and reducing systematic uncertainties. Leavitt's discovery transformed astronomy. Before her work, estimating distances beyond the Milky Way was largely guesswork. Afterward, astronomers had a tool capable of reaching nearby galaxies with reasonable accuracy. Edwin Hubble used Cepheids to establish that the Andromeda Nebula was a galaxy separate from our own, ending the great debate of the early 20th century about the nature of spiral nebulae. He later used Cepheids to correlate distance with redshift, establishing the expansion of the universe. Historians still argue whether Leavitt received sufficient credit during her lifetime. She died in 1921, before Hubble's discoveries made her period luminosity relation famous. Webb observes Cepheids in galaxies where Type Ia supernovae have also occurred, providing a crucial link in the distance ladder. The logic works like this. Calibrate Cepheid distances in nearby galaxies with geometric methods such as parallax, then use Cepheids in more distant galaxies to anchor the absolute luminosities of Type Ia supernovae. Then use those supernovae to reach cosmological distances where redshift and the Hubble constant can be measured directly. Each rung depends on the previous one, so errors propagate unless controlled meticulously. Hubble Space Telescope struggled with Cepheids in crowded stellar fields. In the dense cores of distant galaxies, individual stars blur together, making photometric measurements noisy. Dust in those galaxies absorbs and reddens visible light, further complicating matters. Webb's infrared cameras alleviate both problems. Longer wavelengths suffer less extinction from dust, and Webb's sharper resolution separates stars that Hubble merged into confused blobs. The result? Cleaner light curves, more accurate period determinations, tighter constraints on Cepheid luminosities. Early Webb observations targeted galaxies hosting well-studied Type Ia supernovae, providing independent checks on Hubble-era measurements. The results confirmed previous distance ladder values of H0, not by copying Hubble's data, but by redoing the analysis with superior instruments. If systematic errors had plagued Hubble's Cepheid photometry, Webb should have revealed discrepancies. Instead, Webb found consistency, implying that the Hubble tension cannot be blamed on faulty Cepheid data. The distance ladder stands firm, or at least firmer than critics hoped. There is a quirky detail worth savouring. Cepheid periods range from about 1 day to over 100 days, with the longer period Cepheids being brighter and rarer. Measuring their pulsation requires observing them multiple times over weeks or months, watching their light curves trace sinusoidal or sawtooth patterns. Observers schedule telescope time carefully to catch Cepheids at various phases, building up the data needed for accurate period determination. Webb's scheduling constraints add complexity. It orbits Lagrange point 2 and cannot point at all parts of the sky at all times. Nevertheless, mission planners carved out observing windows to monitor Cepheids in target galaxies, demonstrating the flexibility and dedication required for precision cosmology. Beyond the distance ladder, Cepheids interest astrophysicists for their own sake. These stars occupy a specific region of the Hertzsprung-Russell diagram, known as the instability strip, where certain stellar parameters conspire to drive pulsation through a mechanism involving partial ionization of helium. Understanding why Cepheids pulsate enriches stellar evolution theory and provides independent constraints on stellar physics. Webb's observations contribute to this broader scientific context, not merely serving as cosmological tape measures, but also as laboratories for stellar astrophysics. The distance ladder Cepheids anchor does not end with Type Ia supernovae. Other standard candles extend the reach, the tip of the red giant branch, surface brightness fluctuations in elliptical galaxies, and mirror variables are among the tools astronomers employ. Each method has strengths and weaknesses, and comparing results across methods tests for systematics. Webb has contributed to several of these comparisons, observing red giant populations in nearby galaxies and cross-checking against Cepheid-based distances. So far, the results align, which either means the methods are reliable or that they share common systematics, a possibility always worth considering. There is a philosophical dimension to trusting standard candles. The entire enterprise assumes that physics operates uniformly across cosmic distances and epochs. A Cepheid in a galaxy 50 megaparsecs away obeys the same period. Luminosity relation as a Cepheid in the Milky Way and a Type Ia supernova at redshift 1 produces the same peak luminosity as one nearby. These assumptions are well tested and supported by theory, but they remain assumptions. If stellar physics varied in subtle ways across the universe, different metallicities, different magnetic fields, different environments, standard candles could mislead. Webb's data so far support the uniformity assumption, but vigilance remains warranted. Tonight, let Cepheids pulse gently in your imagination, stellar heartbeats marking time across the cosmos. Henrietta Leavitt identified the pattern over a century ago, using photographic plates and painstaking measurements. Webb continues her legacy with digital detectors and infrared optics, refining the beat she first heard. The distance ladder she helped build now stretches to the edge of the observable universe, rung by rung, photon by photon. Rest your thoughts on that continuity. Past scientists enabling present discoveries enabling future understanding. The ladder keeps climbing, and Webb has added new rungs with gold-coated mirrors. You encounter now a paradox as puzzling as any Webb has revealed. Supermassive black holes that appeared in the universe before there was seemingly enough time for them to grow. These cosmic gluttons containing millions or billions of solar masses crammed into regions smaller than our solar system challenge formation theories and hint at exotic processes in the early universe. Black holes form when massive stars exhaust their nuclear fuel and collapse under gravity. The cores implode, sometimes producing neutron stars, sometimes creating stellar mass black holes, typically ranging from a few to a few tens of solar masses. These stellar remnants can grow by accreting surrounding matter or merging with other compact objects, but growth takes time. Matter falling into a black hole releases energy that heats surrounding gas, creating outward pressure that limits the accretion rate. This limit, known as the Eddington limit, sets a speed ceiling for black hole growth, and even at maximum speed, building a billion solar mass black hole from a stellar mass seed requires hundreds of millions to billions of years. Webb has detected supermassive black holes in galaxies at redshifts above 6, corresponding to epochs less than 1 billion years after the Big Bang. Some of these black holes appear to weigh hundreds of millions of solar masses. If they grew from stellar seeds at the Eddington limit, they would need more time than the universe provided. The math does not work, and astronomers are scrambling to explain the discrepancy. Several formation scenarios have been proposed. One involves direct collapse, in which massive gas clouds in the early universe bypass the normal star formation process and collapse directly into intermediate mass black holes weighing tens of thousands of solar masses. These heavier seeds would require less growth to reach supermassive status, easing the time constraint. Direct collapse requires special conditions, pristine gas free of heavy elements that would otherwise fragment into smaller clumps, and theoretical models struggle to produce enough such events to account for the observed black hole population. Another scenario invokes primordial black holes, objects formed not from stellar collapse, but from density fluctuations in the very early universe, within the first second after the Big Bang. If regions of space were sufficiently overdense during that era, gravity could have overwhelmed the expansion and collapsed those regions into black holes before any stars existed. Primordial black holes could have masses ranging from negligible to enormous depending on the conditions of their formation, and they would serve as ready-made seeds for later growth. This scenario remains speculative. Observational evidence for primordial black holes is limited, and constraints from various experiments exclude certain mass ranges. A third possibility involves super-Eddington accretion, periods during which black holes grew faster than the nominal limit. If gas feeding a black hole is geometrically thick and optically thick, outgoing radiation might become trapped, allowing matter to fall in at rates exceeding the classical Eddington limit. Simulations suggest such phases are possible, but require specific conditions and are probably short-lived. Whether super-Eddington episodes were common enough in the early universe to explain Webb's observations remains an open question. Webb's spectroscopic capabilities have enabled detailed studies of these early black holes. By analysing emission lines from gas swirling near black hole event horizons, astronomers estimate masses and accretion rates with unprecedented precision for high redshift objects. the data confirm that some early black holes are indeed as massive as nearby quasars, not illusions caused by gravitational lensing or misidentified sources. The problem is real, and theorists are paying attention. Historians of black hole research note that surprises have been the norm. Black holes were once theoretical curiosities, dismissed by some physicists as mathematical pathologies rather than physical objects. Their acceptance required decades of observation, including the detection of X-ray binaries, quasars, and eventually gravitational waves from merging black holes. The discovery of supermassive black holes in the early universe continues this tradition of empirical shocks revising theoretical expectations. There is a delightful irony in the situation. Black holes are defined by their invisibility. Nothing, not even light, escapes beyond the event horizon. Yet Webb detects them indirectly, through the brilliant light emitted by matter spiraling inward just before crossing that point of no return. The infalling gas heats to millions of degrees, radiating furiously across the electromagnetic spectrum, including the infrared wavelengths Webb excels at capturing. In a sense, black holes advertise their presence by the chaos they create in their neighbourhoods, glowing beacons of destruction visible across billions of light years. What do these overgrown black holes mean for the broader picture of cosmic evolution? They suggest that the early universe was more violent and dynamic than orderly models assumed. Structure formed rapidly, not just in galaxies but in the dense cores where black holes lurk. The feedback from active galactic nuclei, jets and outflows powered by black hole accretion, may have influenced galaxy evolution more profoundly in early epochs than previously understood, suppressing or enhancing star formation depending on circumstances. Webb's observations are feeding into updated simulations that attempt to reconcile the presence of massive black holes with the stellar populations and gas properties of their host galaxies. Tonight, let the image of an early supermassive black hole settle into your mind. Imagine a whirlpool of gas and radiation, a gravitational vortex swallowing matter in quantities that dwarf stellar lifetimes. Somewhere in the young universe, these monsters already lurked, defying expectations, growing at rates that puzzle theorists. Webb caught their light after a journey of 13 billion years, infrared photons stretched by cosmic expansion, yet carrying information about events that shape the cosmos. Sleep with that mystery, and let it remind you that even the darkest objects leave traces bright enough to cross the universe. You venture now into invisible architecture, the scaffolding of the cosmos built from a substance that interacts with nothing except gravity, dark matter. Webb has illuminated this hidden framework indirectly, tracing its influence through the bending of light and the clustering of galaxies, revealing structures on scales that humble ordinary imagination. Dark matter comprises roughly 27% of the universe's total energy content, outweighing visible matter by a ratio of about 5:1. It does not emit, absorb, or scatter light, making it utterly invisible to telescopes that rely on electromagnetic radiation. Yet its gravitational pull shapes the distribution of galaxies, the rotation of spiral arms, and the dynamics of galaxy clusters. Without dark matter, the universe as we observe it would not exist. Galaxies would fly apart, clusters would never form, and cosmic structure would remain a featureless soup. The evidence for dark matter accumulated over decades. In the 1930s, Fritz Zwicky studied the Coma cluster and noticed that galaxies were moving too fast to be held together by the gravity of visible matter alone. He postulated Dunkel Materie, dark matter, to account for the missing mass. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found that outer stars orbited faster than expected, implying unseen mass in extended halos. Subsequent observations of gravitational lensing, the cosmic microwave background, and large-scale structure confirmed that dark matter is ubiquitous and essential. Historians still argue whether Zwicky's early work received adequate recognition during his lifetime. He was famously cantankerous, which did not endear him to colleagues. Webb contributes to dark matter studies primarily through gravitational lensing observations. When light from a distant galaxy passes near a massive foreground object, another galaxy or a cluster, the space-time curvature bends the light, magnifying and distorting the background source. The degree of bending depends on the total mass of the foreground lens, including dark matter. By analysing the shapes and positions of lensed arcs in deep-field images, astronomers reconstruct the mass distribution of clusters, mapping dark matter concentrations invisible by any other means. Webb's deep fields are littered with gravitational arcs, streaks and smears of light from background galaxies stretched by cluster gravity. The famous first deep field, centered on SMACS 0723, showcases this phenomenon dramatically. Several arcs appear as elongated crescents, some reddened by extreme redshift, others bluer and closer. Each arc encodes information about the mass between the source and the observer. Modelling these arcs is computationally intensive, requiring sophisticated algorithms that infer dark matter distributions from the observed distortions. Webb's sharper images reduce ambiguities, providing cleaner inputs for these reconstructions. The results reveal dark matter arranged in halos surrounding galaxies and filaments, connecting clusters across millions of light-years. The cosmic web, as this structure is called, resembles a three-dimensional spiderweb of dark matter strands, with galaxies clustering at nodes where filaments intersect. Simulations based on lambda CDM predict this web-like structure, and observations confirm its existence. Webb's contribution lies in refining the details, measuring halo masses more precisely, detecting substructure within halos, probing the inner regions where dark matter density peaks. A peculiar property of dark matter is its apparent collisionlessness. When galaxy clusters merge, the visible gas clouds collide and heat up, emitting X-rays. But dark matter halos pass through each other without interaction, their distributions offset from the gas. The Bullet cluster, observed with Hubble and Chandra, provided dramatic evidence of this behaviour. Webb can study similar merging systems in deeper fields, adding data points to the case for dark matter as a particle species distinct from ordinary baryonic matter. What is dark matter made of? Despite decades of effort, no one knows for certain. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles predicted by extensions of the standard model of particle physics. Searches using underground detectors and particle colliders have so far come up empty, ruling out certain WIMP parameter spaces without eliminating the concept entirely. Other candidates include axions, sterile neutrinos, and primordial black holes in specific mass ranges. Webb cannot detect dark matter particles directly, but its observations constrain the properties such particles must have to produce the observed structures. There is a philosophical dimension to dark matter worth pondering. The universe's dominant matter component remains invisible, detectable only through its gravitational effects. We infer its existence much as we infer the wind by watching trees bend. This reliance on indirect evidence does not make dark matter less real, but it does underscore the limits of human perception. The cosmos is not obligated to reveal itself in ways convenient for evolved primates. It simply exists, and we struggle to decode its messages with whatever tools we can devise. Tonight, imagine the dark matter web stretching around you, invisible filaments threading through the space between galaxies, anchoring clusters like dew on a spider's silk. Webb cannot see the filaments directly, but it sees the galaxies clinging to them, the arcs of lensed light-tracing mass distributions, the echoes of a gravitational architecture built long before stars existed. The scaffolding was in place first, and visible matter followed, falling into wells of dark gravity, igniting into stars, coalescing into galaxies. You are part of that visible matter, a fortunate arrangement of atoms embedded in a universe shaped by forces you cannot sense. Rest on that thought, and let the invisible scaffold hold you gently through the night. You move now into one of nature's most elegant optical tricks: gravitational lensing, the bending of light by mass predicted by Einstein's general relativity and exploited by Webb to peer deeper into the cosmos than its mirrors alone could reach. This phenomenon transforms galaxy clusters into cosmic magnifying glasses, revealing faint objects otherwise hidden beyond detection limits. General relativity describes gravity not as a force acting at a distance, but as the curvature of space-time caused by mass and energy. Massive objects warp the fabric of space around them, and light travelling through that warped region follows curved paths. The effect is analogous to a glass lens bending light rays, though the underlying physics differs entirely. Einstein predicted this bending in 1915, and Sir Arthur Eddington confirmed it during a solar eclipse in 1919 by measuring the apparent positions of stars near the sun's edge. That confirmation made Einstein a global celebrity and established general relativity as more than mathematical abstraction. Gravitational lensing manifests in several forms depending on the alignment and masses involved. Strong lensing occurs when a massive foreground object, typically a galaxy cluster, lies almost directly between the observer and a distant background source. The result can be multiple images of the same source, or elongated arcs stretching around the foreground mass like segments of a ring. Webb's deep fields display numerous strong lensing arcs, some so distorted they wrap nearly into complete circles called Einstein rings. Weak lensing is more subtle, involving slight distortions of background galaxy shapes caused by intervening mass along the line of sight. Individually, these distortions are nearly imperceptible, but statistical analysis of thousands of galaxy shapes reveals the underlying mass distribution. Webb contributes to weak lensing surveys by providing sharp images of faint galaxies, improving shape measurements that feed into mass reconstructions. Microlensing involves stellar mass objects, stars or stellar remnants, momentarily magnifying background stars as they pass in front. This technique has detected exoplanets and constrained the abundance of primordial black holes. While Webb's primary focus is not microlensing, its observations complement surveys conducted by other telescopes. Webb exploits strong lensing aggressively. By targeting fields behind massive galaxy clusters, astronomers gain free magnification of background objects, sometimes by factors of 10, 50, or even more. The trade-off is distortion. Lensed images are stretched and curved, requiring sophisticated modelling to reconstruct the original source properties. But the magnification allows detection of intrinsically faint objects that would otherwise require impossibly long exposures. Several of the most distant galaxy candidates identified by Webb owe their detection to gravitational lensing. Without the boost from foreground clusters, their light would be too faint for even Webb's sensitive detectors to register in reasonable exposure times. Lensing transforms these objects from statistical impossibilities into observable targets, pushing the frontier of high redshift astronomy. There is a delightful irony in this arrangement. Galaxy clusters, the largest gravitationally bound structures in the universe, become instruments in their own right, supplementing human technology with natural optics. Astronomers cannot choose where clusters are located or how strongly they lens, but they can select fields that maximize the magnification benefit. Planning observations involves modeling cluster mass distributions, predicting magnification maps, and identifying regions where background sources are most amplified. Historians of astronomy recall that gravitational lensing was once considered a theoretical curiosity, unlikely to be observed. The probability of precise alignment seemed too small, and the angular separations of multiple images too tiny for early telescopes to resolve. The first confirmed gravitational lens was discovered only in 1979, a quasar appearing as two images separated by 6 arc-seconds, lensed by a foreground galaxy. Since then, discoveries have multiplied, aided by surveys and improved instrumentation. Webb represents the latest leap, revealing lensed arcs and multiple images in nearly every deep field it observes. One particularly striking example is the galaxy cluster Abell 2744, nicknamed Pandora's cluster for the complex processes operating within it. Webb's images reveal dozens of lensed background galaxies, some appearing multiple times around the cluster core, others stretched into long arcs that trace the dark matter distribution. Follow-up spectroscopy has identified several extremely high redshift candidates among the lensed sources, pushing cosmic history's frontier closer to the Big Bang. Gravitational lensing also provides tests of general relativity on cosmological scales. If gravity behaved differently than Einstein predicted at large distances, the observed lensing patterns would deviate from models. So far, observations confirm general relativity's predictions to high precision, reinforcing the theory's validity across a remarkable range of conditions. This consistency does not prove general relativity is the final word. Quantum gravity remains an unsolved puzzle, but it demonstrates that Einstein's equations remain reliable tools for cosmology. Tonight, let gravitational lensing become a metaphor as much as a phenomenon. Light from the distant universe bends around obstacles, finding paths to your eyes despite the mass that lies between. The cosmos collaborates in its own observation, mass magnifying light, enabling discoveries that hardware alone could not achieve. Webb's golden mirror collects photons that have been bent, stretched, and redirected across billions of years, photons that carry information about both the sources that emitted them and the masses that deflected them. In that collaboration lies a kind of cosmic generosity, the universe offering magnification as a gift to curious observers. Rest with that gift, and let the curved paths of ancient light guide you gently towards sleep. You approach now the boundary of the known, the edge of the observable universe, and confront the staggering scale that Webb has helped illuminate. This edge is not a wall or a barrier, but a horizon, defined by the finite speed of light and the age of the cosmos, a limit beyond which photons have not had time to reach us. The observable universe has a diameter of roughly 93 billion light-years. That number deserves a pause. A single light-year spans about 9.46 trillion kilometers, the distance light travels in 1 year. Multiply that by 93 billion, and you approach a quantity so vast that human intuition simply fails. The entire history of human civilization, agriculture, writing, empires, science, fits comfortably within a few tens of thousands of years, a cosmic eye blink. The observable universe contains structures whose light began its journey when Earth did not exist, when the sun was merely a cloud of gas that had not yet collapsed. Why 93 billion light-years if the universe is only about 13.8 billion years old? The answer lies in cosmic expansion. Light from the most distant objects departed when those objects were much closer to us. During the photon's journey, space expanded, stretching the distance between source and observer. By the time the light arrives, the source has receded far beyond its original position, carried by the expansion of space itself. The 93 billion light-year figure accounts for this expansion, representing the current distance to objects whose light is just now reaching us. Webb observes objects at redshifts above 10, corresponding to look-back times exceeding 13 billion years. These are among the oldest photons accessible to any telescope, emitted when the universe was less than 5% of its current age. The sources of those photons are now incredibly distant, tens of billions of light-years away, receding at speeds exceeding light due to the cumulative expansion. We cannot see them as they are now. We see only the ancient images captured in photons that began their journey in a younger, smaller cosmos. Beyond the observable universe lies more universe. There is no physical boundary marking the edge of existence, only a horizon imposed by the finite speed of light. Photons from beyond the horizon have not had time to reach us, and depending on the geometry and fate of the cosmos, they may never arrive. Some cosmologists speculate that the total universe is vastly larger than the observable portion, perhaps infinitely so, stretching endlessly with structure similar to what we observe, or perhaps radically different, with varying physical constants or even different laws. Webb cannot peer beyond the horizon, but it pushes our vision remarkably close to the limit. The cosmic microwave background, released roughly 380,000 years after the Big Bang, marks a kind of opaque wall beyond which photons could not travel freely. Before recombination, the universe was a hot plasma scattering light incessantly. Only after recombination did space become transparent, allowing photons to stream unimpeded. Webb observes galaxies and structures formed after the microwave background, filling in the gap between that primordial afterglow and the mature galaxies we see nearby. Each high redshift detection narrows that gap, approaching but never reaching the moment of the Big Bang itself. There is a profound philosophical dimension to contemplating cosmic scale. The numbers, billions of galaxies, trillions of stars, quintillions of planets, exceed human experience and resist emotional comprehension. Yet here you are, a configuration of atoms contemplating configurations of atoms across unfathomable distances, connected by photons that crossed voids where nothing else travelled. The scale does not diminish you, it contextualizes you. You're not small in a pejorative sense, but located in a vast relational web, part of a universe that includes both the infinitesimal and the immense. Historians of cosmology trace the expansion of human awareness in stages. Ancient cultures imagined the cosmos as a dome above a flat Earth, contained and comprehensible. Copernicus displaced Earth from the centre, and subsequent centuries revealed first the solar system, then the galaxy, then the multitude of galaxies beyond. Each stage expanded the known universe and shrank humanity's apparent centrality. Webb represents the latest stage, pushing the frontier to redshifts unimaginable a generation ago, revealing a cosmos more crowded and ancient than any previous instrument could show. There is a quirky irony in calling it the observable universe. The term implies that observation exhausts its subject, that once seen, the universe is known. In reality, observation reveals more questions than answers. Webb's images show galaxies whose properties puzzle theorists, black holes whose origins confound models, expansion rates that refuse to agree. Observation is not a destination but a process, each answered question spawning new uncertainties. The observable universe is not a solved equation but an ongoing investigation. Tonight, let the scale settle gently rather than overwhelm. 93 billion light-years of diameter, hundreds of billions of galaxies, photons travelling since before Earth existed. These facts do not require emotional processing. They simply exist, part of the furniture of reality whether or not you dwell on them. Webb shows us what is, and what is turns out to be astonishingly vast. Rest your mind on that vastness, not as a burden, but as a backdrop. You're part of this cosmos, an arrangement of stellar ash that briefly contemplates the furnace from which it came. sleep well, knowing the universe extends far beyond any dream you might have, and dreams are nonetheless possible because stars once exploded and scattered their elements across space. You drift now into stellar nurseries, the glowing cradles where new suns are born, shrouded in gas and dust but revealed in breathtaking detail by Webb's infrared vision. These regions, once opaque to optical telescopes, now blaze with colour and complexity, painting portraits of creation that redefine our understanding of how stars come to be. The most famous of Webb's stellar nursery images depicts the Carina Nebula, a vast cloud of gas and dust about 7,600 light-years from Earth. Hubble had imaged Carina before, revealing towering pillars of dense material sculpted by radiation from nearby hot stars. Webb's infrared view penetrates deeper, showing previously hidden structures within the pillars, baby stars wrapped in cocoons of dust, jets of material streaming from protostars, cavities carved by stellar winds. The image resembles a cosmic cliff, a rugged shoreline where starlight erodes mountains of gas, and the metaphor is not entirely fanciful. Radiation pressure from massive stars does sculpt these structures, driving shock waves that compress gas and trigger new rounds of star formation. Star formation begins when a dense region within a molecular cloud collapses under gravity. The collapse is not uniform. Turbulence and magnetic fields fragment the cloud into smaller clumps, each potentially becoming a separate star or star system. As a clump contracts, conservation of angular momentum spins it into a disk, and material spirals inward, feeding the growing protostar at the center. Eventually, the core heats enough to ignite nuclear fusion, and a star is born. The entire process takes millions of years, a blink by cosmic standards, but an eternity by human reckoning. Webb's contribution lies in observing the earliest, most deeply embedded phases of this process. Optical telescopes see only the surfaces of molecular clouds, the illuminated edges where starlight escapes. Infrared wavelengths penetrate the dust, revealing protostars still accreting mass, protoplanetary disks where planets may be forming, and outflows that carry away angular momentum and allow collapse to continue. Without infrared capability, these crucial stages remained hidden, like trying to understand pregnancy by examining only the delivery room. The detail Webb achieves is remarkable. In images of the Orion Nebula, another famous stellar nursery about 1,300 light-years away, Webb resolved individual protoplanetary disks, flattened structures of gas and dust surrounding young stars. Some disks appear edge-on, their dust lanes dark silhouettes against brighter backgrounds. Others appear face-on, showing spiral patterns that hint at embedded planets or gravitational instabilities. These disks are the raw material from which planetary systems form. Studying them illuminates the processes that built our own solar system billions of years ago. Webb also detected objects too small to be stars but too large to be planets. Brown dwarfs, sometimes called failed stars, that lack sufficient mass to sustain hydrogen fusion. Brown dwarfs glow faintly in infrared, warmed by residual heat from their formation, and, in some cases, by deuterium fusion in their cores. Webb's surveys of stellar nurseries have identified numerous brown dwarf candidates, refining estimates of their abundance and probing the lower mass limits of star formation. Some of these objects may be accompanied by even smaller companions, exomoons or perhaps rogue planets ejected from forming planetary systems. There is a poetic quality to stellar nurseries that transcends scientific description. Stars are born in groups, siblings emerging from the same cloud, sharing material and momentum before dispersing into the galaxy. The Sun likely formed in such a cluster, its birth companions now scattered across the Milky Way, untraceable after billions of years of orbital drift. Webb's images capture this communal origin, showing clusters of young stars embedded in the same glowing nebulae, their fates intertwined for a few million years before they go their separate ways. Historians of astronomy note that stellar nurseries were among the first deep sky objects catalogued by early observers. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, has been known for centuries, though its nature as a star-forming region was not understood until the 20th century. Charles Messier included several nebulae in his famous catalogue of objects to avoid while hunting comets, inadvertently creating a list that amateur astronomers still cherish. Webb continues this tradition of cataloguing, adding infrared detail to objects observed for generations. The colours in Webb's nursery images deserve a note of explanation. Infrared light is invisible to human eyes, so the images are false colour representations, with different infrared wavelengths mapped to visible colours. Shorter infrared wavelengths might appear blue, longer ones red, creating vivid but artificial palettes. The choices are not arbitrary. They're designed to highlight scientific features and create aesthetically pleasing images. Some purists grumble about false colour, but the practice has a long history in astronomy, and the alternative, publishing images in shades of grey, would deprive the public of much visual wonder. Tonight, let the nursery images settle gently into your mind. Pillars of creation rising from cosmic dust. Protostars glowing like embers in dark caverns. Disks of gas spinning around infant suns, perhaps forming planets as you listen. The universe is not static. It is constantly creating, constantly renewing itself with fresh stars and the promise of new worlds. You're made of elements forged in stars that died before the sun was born, and somewhere tonight, new stars are igniting that will seed future generations of matter. Rest on that continuity and let the slow, patient rhythm of star formation lull you towards sleep. The nurseries will still be there when you wake, quietly building the next generation of cosmic light. Now, as we approach the gentle end of this section, let the imagery soften like distant starlight diffusing through a nebula's veil. The pillars of creation stand not as monuments to chaos, but as cathedrals of becoming, where gravity and time conspire to kindle new flames against the dark. You have travelled far tonight, from the golden mirror unfurling at Lagrange point 2 to the earliest galaxies and the puzzles they pose through the mathematics of redshift and the tension of expansion rates, past black holes that grew too fast and dark matter that shapes everything unseen. Now you rest in the cradle where stars are born, surrounded by gas that will one day become planets, moons, perhaps even life. Let your breathing slow to match the pace of cosmic processes, millions of years compressed into the rhythm of your lungs. The universe does not hurry, and neither should you. The questions raised tonight will persist beyond your sleep, tended by astronomers and theorists who wake while you dream, but the wonder belongs to anyone who pauses to look upward. Webb's images are gifts, translated from infrared into colours you can see, from data into stories you can hear. They ask nothing of you except attention, and even that is optional. The cosmos continues whether or not you contemplate it, but contemplating it enriches the cosmos, adding a layer of awareness to the unfolding. So close your eyes now if they are not already closed. Let the stellar nurseries fade into soft abstraction, colours blurring into warmth blurring into stillness. You're safe here, wrapped in the ordinary gravity of Earth, breathing ordinary air made of extraordinary atoms. The same processes that birthed distant suns once birthed the sun that warms your world, and the continuity stretches backward and forward beyond reckoning. Sleep is its own kind of creation, a daily renewal of mind and body, and you have earned it by journeying so far tonight. Rest well, dream gently, and know that the universe holds you as it holds everything, patiently, indifferently, magnificently. The light will still be falling when you wake, ancient photons arriving on schedule, carrying news from epochs before memory. Until then, let the silence of space become the silence of sleep and drift. You awaken gently into a new domain, one where the air you might breathe does not exist on Earth, but on worlds orbiting distant stars. Webb has begun to taste the atmospheres of exoplanets, revealing molecular signatures that transform these alien worlds from statistical blips into places with weather, chemistry, and the faint possibility of biology. Exoplanet science has progressed astonishingly far since the first confirmed detection around a Sun-like star in 1995. That world, 51 Pegasi b, was a hot Jupiter, a gas giant orbiting so close to its star that its year lasted only 4 days. It upended expectations. Prior to its discovery, most astronomers assumed planetary systems would resemble our own, with small rocky worlds close in and gas giants farther out. 51 Pegasi b announced that the universe had other ideas, and subsequent surveys revealed a dizzying diversity of planetary architectures: super-Earths, mini-Neptunes, eccentric giants, tightly packed multi-planet systems, and worlds orbiting binary stars. Finding exoplanets is one thing, characterizing them is another. Until recently, most exoplanets were detected indirectly, either by the gravitational wobble they induce in their host stars, or by the dimming caused when they transit across the stellar disk. These methods reveal orbital parameters and sometimes radius or minimum mass, but they say little about what the planets are made of or what their atmospheres contain. Webb changes that calculus by enabling transmission spectroscopy at infrared wavelengths with unprecedented sensitivity. Transmission spectroscopy works like this. When an exoplanet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere, acquiring absorption signatures from molecules present in the upper layers. By comparing the spectrum during transit to the spectrum when the planet is absent, astronomers isolate the atmospheric contribution. Different molecules absorb at different wavelengths. Water vapor, carbon dioxide, methane, ammonia, sodium, potassium, each leaving a characteristic fingerprint. Webb spectrographs capture these fingerprints across a broad infrared range, detecting molecules that shorter wavelength instruments miss. One of Webb's early headline results involved WASP-39b, a hot Saturn about 700 light-years away. Webb detected carbon dioxide in its atmosphere, the first unambiguous identification of this molecule in an exoplanet. Carbon dioxide is significant because it is a common product of geological and biological processes on Earth. Finding it elsewhere demonstrates that planetary chemistry is not unique to our solar system. Webb also detected water vapor, sulfur dioxide, and hints of clouds in WASP-39b's atmosphere, painting a picture of a world with active chemistry driven by intense stellar radiation. The sulfur dioxide detection was particularly surprising. This molecule forms when sulfur compounds react with oxygen-rich radicals in the presence of ultraviolet light. Its presence on WASP-39b indicates photochemistry, reactions driven by starlight rather than internal heat. Understanding photochemistry on exoplanets helps constrain atmospheric models and predict what signatures might appear on potentially habitable worlds. Webb has also observed several smaller, cooler exoplanets, edging closer to the rocky Earth-like regime. The TRAPPIST-1 system, which we will explore in the next section, has received particular attention. But even before TRAPPIST-1 data arrived, Webb demonstrated that transmission spectroscopy could probe atmospheres of planets only a few times Earth's mass, opening a frontier that Hubble could barely glimpse. The sensitivity improvements are not incremental, they are transformational, turning previously impossible measurements into routine observations. There is a quirky historical footnote worth mentioning. The term exoplanet was not always standard. Early literature referred to extrasolar planets, or simply planets around other stars. The abbreviation EXO gained traction in the 1990s and 2000s, mirroring exobiology, the study of life beyond Earth. Language shapes perception, and naming these worlds as exoplanets framed them as a category worthy of dedicated study rather than mere anomalies. Historians of science note that nomenclature often follows, rather than precedes, conceptual shifts. Once exoplanets became a recognized field, the vocabulary solidified. What does tasting an exoplanet atmosphere feel like? The metaphor is imperfect but evocative. Webb captures photons that pass through alien skies, absorbing some wavelengths, transmitting others, carrying information about molecular abundances and temperature profiles. That information travels across light years, collected by a golden mirror, dispersed by spectrographs, analysed by algorithms, and interpreted by human minds. The distance between measurement and experience is vast, yet the connection is real. We know something about what WASP-39b's air contains, something that no human will ever directly sense, but that nonetheless enriches our map of the cosmos. The ultimate goal of exoplanet atmosphere characterization is the search for biosignatures, molecular combinations that might indicate life. Oxygen and methane together, for instance, are chemically unstable and would require a continuous source to coexist, possibly biology. Ozone, a byproduct of oxygen, absorbs ultraviolet light in ways that could be detected spectrally. Nitrous oxide, dimethyl sulfide, and other trace gases have been proposed as potential biosignatures depending on context. Webb is not designed to confirm life, but it is designed to identify worlds where life might be worth looking for, narrowing the search from billions of candidates to a manageable few. Tonight, let the molecular fingerprints drift through your imagination. Water vapor condensing on alien clouds, carbon dioxide cycling through volcanic eruptions and atmospheric escape, sulfur compounds reacting in the glare of a foreign sun. These are not fictions but measured realities, data points in the expanding catalogue of planetary chemistry. Webb has begun to read the atmospheres of other worlds, and the alphabet it uses is spectroscopy. Rest with that thought, and let the distant skies of exoplanets blend into the familiar ceiling above your bed. You arrive now at a particular star system that has captured the imagination of scientists and dreamers alike. TRAPPIST1, a cool red dwarf orbited by 7 rocky planets, 3 or 4 of which reside in the habitable zone where liquid water might persist on the surface. Webb has turned its gaze toward this system, and the early results are reshaping expectations about what habitability might require. TRAPPIST-1 lies about 40 light-years from Earth, a cosmic neighbour by any reasonable measure. The star itself is small and dim, an ultra-cool dwarf with a mass roughly 9% that of the Sun, and a luminosity less than 1% of solar output. Its 7 planets orbit much closer than Mercury orbits our Sun, with orbital periods ranging from about 1.5 to nearly 19 days. The proximity keeps the planets warm despite the star's feeble output, but it also subjects them to intense stellar activity, flares, ultraviolet radiation, and charged particle bombardment that might strip atmospheres or irradiate surfaces. The TRAPPIST-1 planets are named alphabetically from B to H, with B being the innermost and H the outermost. Planets D, E, and F occupy the habitable zone, the region where surface temperatures might allow liquid water under the right atmospheric conditions. Planet E has drawn particular attention because its size and density suggest a rocky composition similar to Earth, and its position in the habitable zone makes it a prime candidate for atmosphere studies. Webb observed TRAPPIST-1b and C in its first year, focusing on thermal emission rather than transit spectroscopy. By measuring the infrared light emitted by these planets as they pass behind the star secondary eclipse, astronomers can estimate surface or dayside temperatures and infer whether significant atmospheres are present. A thick atmosphere would redistribute heat, reducing the temperature contrast between day and night sides. A thin or absent atmosphere would leave the day side scorching and the night side frigid. The results for TRAPPIST-1b were sobering. Thermal emission measurements indicated a dayside temperature consistent with bare rock absorbing and re-radiating stellar energy, with no evidence of significant heat redistribution. This suggests that TRAPPIST-1b lacks a substantial atmosphere, its original gases likely stripped by stellar radiation over billions of years. The finding was not entirely unexpected. TRAPPIST-1b orbits closest to the star and receives the most intense radiation, but it tempered hopes that all 7 planets might harbour hospitable skies. TRAPPIST-1c showed similar patterns, with thermal emission suggesting minimal atmospheric insulation. Again, the innermost planets appear to have lost whatever atmospheres they might have possessed, casualties of their star's violent youth and ongoing activity. Red dwarfs are notorious for flares, especially in their first billion years, and TRAPPIST-1's planets have been orbiting in that harsh environment for approximately 7 billion years. The cumulative radiation exposure may have been too much for inner planet atmospheres to survive. What about the habitable zone planets D, E, and F? Webb observations are ongoing, and results have been slower to emerge because these planets are cooler and emit less thermal radiation, requiring longer exposures or different observational strategies. Transit spectroscopy offers another avenue, probing up atmospheres for molecular signatures during transits. Early indications are ambiguous. Some datasets hint at flat, featureless spectra, which could indicate thick clouds, airless surfaces, or simply insufficient signal-to-noise. Astronomers are collecting more data, refining analyses, and preparing for follow-up observations that may clarify the picture. There is a peculiar emotional quality to following TRAPPIST-1 results. The system has become a symbol of the search for habitable worlds, featured in countless articles, videos, and even a NASA travel poster depicting imaginary tourism. The attachment is understandable. 7 rocky planets around a nearby star feels like a jackpot, a natural laboratory for testing ideas about planetary evolution and habitability. But attachment can lead to disappointment when reality intrudes, and the early Webb results remind us that habitability is not guaranteed by location alone. Historians of exoplanet science recall similar emotional arcs. The discovery of planets around pulsars in 1992 excited researchers until it became clear those worlds formed from supernova debris inhospitable by any definition. The first Earth-sized planet in a habitable zone, Kepler 186f, generated headlines but remains too distant for atmospheric characterization with current technology. TRAPPIST. One offered hope that atmospheric studies would be feasible, and they are, but the atmospheres may not be there. Still, the story is not over. Outer planets D, E, and F may have retained gases that inner planets lost, protected by greater distances and lower radiation doses. Volcanic outgassing, cometary impacts, or other processes might have replenished atmospheres over time. The next few years of Webb observations will test these possibilities, and upcoming missions like the Habitable Worlds Observatory may push characterization further. Science is patient, and TRAPPIST-1 will remain a target for decades. Tonight, let the 7 worlds of TRAPPIST-1 orbit gently in your imagination. Close together, tidally locked, bathed in the ruddy glow of their small star, Some may be barren rock. Others may hide surprises beneath thick clouds or thin hazes. The distance, 40 light-years, is simultaneously immense and trivial, far beyond any spacecraft we could currently build, yet practically next door by cosmic standards. Webb has begun to read their stories, and the chapters so far are cautionary but not conclusive. Rest with that uncertainty and let the red dwarf's faint light flicker at the edge of your dreams. You wade now into the most tantalizing question Webb might help answer, even if a definitive answer remains beyond its reach: the search for biosignatures, molecular hints that life might exist beyond Earth. This is the Grail quest of exoplanet science, and Webb has equipped the questers with better tools than they have ever possessed. A biosignature is any observable phenomenon that suggests biological activity. On Earth, the most obvious atmospheric biosignature is oxygen, produced primarily by photosynthesis. Oxygen is reactive. Without continuous replenishment, it would combine with surface rocks and disappear from the atmosphere within a few million years. Its presence indicates an ongoing source, and on Earth, that source is life. Methane is another candidate, especially when found alongside oxygen, because the two molecules react and destroy each other, implying separate sources must be actively producing both. Webb can detect oxygen indirectly through ozone, which absorbs strongly at certain infrared wavelengths. Ozone forms from oxygen via photochemical reactions, so its presence implies oxygen in the atmosphere. Methane absorbs at wavelengths well within Webb's range, making it a primary target for biosignature searches. Carbon dioxide, water vapor, and other molecules provide context, helping distinguish biological signals from geological or photochemical mimics. The challenge is interpretation. Oxygen can be produced abiotically through photolysis of water vapor, where ultraviolet light splits water molecules and hydrogen escapes to space, leaving oxygen behind. This process might occur on planets around active M-dwarf stars like TRAPPIST-1, generating oxygen without any biology involved. Methane can emerge from volcanic outgassing or serpentinization, chemical reactions between water and rock that require no living organisms. Disentangling biological from non-biological sources requires understanding a planet's full context: its star, its geology, its atmospheric chemistry, its history. Webb's role is not to confirm life, but to identify planets worth further investigation. If transmission spectroscopy reveals a rocky planet with water vapor, oxygen or ozone, and methane in proportions difficult to explain without biology, that planet becomes a priority for future missions. Confirmation would require follow-up with larger telescopes, perhaps direct imaging that could detect seasonal changes or geographic variations indicating active biospheres. Webb opens doors. Future missions walk through them. There is a philosophical dimension to biosignature detection worth contemplating. Humans have wondered about life beyond Earth for millennia, from ancient speculations about lunar inhabitants to modern SETI efforts listening for radio signals. The search for biosignatures via spectroscopy represents a different approach: passive observation of chemistry rather than active communication. If we detect biosignatures on an exoplanet, we will not be conversing with alien intelligence. We will be inferring the presence of microbes or plants through their metabolic byproducts. The confirmation would be profound but indirect, like deducing a forest fire from smoke seen across a valley. Some scholars argue that the detection of any extraterrestrial life, even microbial, would constitute the most significant scientific discovery in human history. Others caution that the philosophical and societal implications are uncertain, and that premature claims could damage public trust in science. The history of Mars exploration offers lessons. Early announcements of possible Martian fossils in a meteorite generated excitement, followed by skepticism. and the question of life on Mars remains open despite decades of robotic exploration. Webb's exoplanet observations will face similar scrutiny, and astronomers are acutely aware of the need for rigour. A quirky aspect of biosignature research involves false positives and false negatives. A false positive occurs when abiotic processes mimic biological signatures, leading to erroneous claims of life. A false negative occurs when life exists but does not produce detectable signatures, perhaps because it uses unfamiliar biochemistry or resides in subsurface environments shielded from observation. Webb's observations will generate candidate biosignatures that must be evaluated against these possibilities, a process requiring collaboration among astronomers, chemists, geologists, and biologists. Webb has already contributed to this effort by refining atmospheric models and expanding the catalogue of observed exoplanet spectra. Each new observation tests theoretical predictions and calibrates detection thresholds. The absence of biosignatures in early targets is not discouraging. It narrows the search and improves understanding of what to look for. Science often progresses through exclusion, eliminating possibilities until what remains, however improbable, must be considered. Tonight, let the search for biosignatures hover gently at the edge of your consciousness. Somewhere perhaps, on a world orbiting a star you cannot see with naked eyes, chemistry is happening that might be life. Webb is sniffing the atmospheres of distant planets, sorting molecules, building a database that future generations will mine for patterns. The answer may come in your lifetime or long after. The search itself is valuable, a testament to human curiosity and ingenuity. Rest with that thought, and let the possibility of life elsewhere in the cosmos accompany your dreams without demanding resolution. The universe keeps its secrets patiently, and patience is a virtue you can practice tonight. You turn now to cosmic chemistry, the processes by which the universe built the heavy elements that compose planets, oceans, and living beings. Webb traces this chemical history across billions of years, observing the stellar explosions and collisions that forge elements heavier than iron, connecting your atoms to ancient cataclysms. The lightest elements, hydrogen, helium, and traces of lithium, were created in the first few minutes after the Big Bang, during a brief epoch of nucleosynthesis when the universe was hot and dense enough for nuclear reactions. Everything else came later, manufactured inside stars or during their violent deaths. Carbon, oxygen, nitrogen, silicon, sulfur, the building blocks of rocky planets and organic molecules, were fused in the cores of massive stars over millions of years, then dispersed when those stars exploded as supernovae. Supernovae are cosmic recyclers. When a massive star exhausts its nuclear fuel, its core collapses, triggering a shock wave that blows the outer layers into space at thousands of kilometers per second. The explosion synthesizes additional elements through rapid neutron capture, a process called the R process, and scatters both pre-existing and newly forged nuclei across the interstellar medium. Subsequent generations of stars incorporate this enriched material, and the cycle continues, each generation slightly richer in heavy elements than the last. Webb contributes to this story by observing supernovae and their remnants across cosmic history. Spectroscopy reveals the abundances of elements in the expelled gas, testing nucleosynthesis models and tracing chemical evolution. High redshift observations show how element abundances change over time, comparing early galaxies with relatively pristine composition to later galaxies enriched by billions of years of stellar processing. But supernovae are not the only forgers. Neutron star mergers, discovered gravitationally in 2017, with the event GW 170817, produce even heavier elements through extremer process nucleosynthesis. When two neutron stars spiral together and collide, They release neutron-rich material that rapidly captures neutrons, building nuclei up through the periodic table to gold, platinum, uranium, and beyond. The collision also produces a kilonova, a bright transient powered by radioactive decay of freshly synthesized heavy elements. Webb's infrared sensitivity makes it ideal for observing kilonovae, capturing the glow of heavy element decay in events too faint for optical telescopes. In 2023, Webb observed the afterglow of a gamma-ray burst, GRB 230307A, and detected spectral signatures consistent with heavy element production, likely from a neutron star merger. The observation provided direct evidence that mergers contribute significantly to the cosmic inventory of R-process elements, confirming theoretical predictions and adding a data point to the ongoing debate about the relative contributions of supernova and mergers. There is a poetic symmetry in this chemistry. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar interiors or explosive events billions of years ago. You are quite literally stardust, a phrase so often repeated that it risks becoming cliché. But Webb makes the phrase tangible by showing the factories at work, the supernovae and kilonovae that built the elements now assembled into your body. The connection is not metaphorical but physical, a chain of causation stretching from ancient explosions to your present existence. Historians of chemistry note that the stellar origin of elements was not established until the 20th century. Before that, the periodic table was a catalogue without a creation story, elements classified by properties but not by provenance. Fred Hoyle, William Fowler, and the husband-wife team of Geoffrey and Margaret Burbidge published a landmark paper in 1957, often called B2FH, that laid out nucleosynthesis pathways in detail, explaining how stars build elements through fusion and how supernovae disperse them. That paper remains foundational, though subsequent discoveries, including the role of neutron star mergers, have expanded the picture. Webb's observations of chemical evolution have practical implications beyond curiosity. Understanding how elements accumulate over cosmic time helps constrain models of planet formation and habitability. Life as we know it requires certain elements in certain abundances. If the early universe lacked sufficient carbon or oxygen, planets suitable for life could not have formed. Webb's high redshift spectroscopy suggests that heavy element enrichment proceeded rapidly, with some early galaxies showing surprising metal abundances. This rapidity is another puzzle for theorists, related to the unexpectedly early galaxies discussed earlier. Tonight, let the cosmic chemistry settle into your awareness. Every atom in your body has a history stretching back billions of years, a journey through collapsing clouds, igniting cores, explosive deaths, and drifting debris. Webb captures snapshots of that journey, infrared photons carrying information about element abundances in distant stars and galaxies. The connection between those photons and your cells is indirect but real, a causal chain written in nuclear physics and cosmic evolution. Rest with that connection, and let the ancient forges of the universe warm your thoughts as you drift towards sleep. You step now into the ongoing rewrite of galaxy evolution, a textbook revision driven by Webb's ability to compare infant universe snapshots with mature galaxies nearby. The life cycle of galaxies, their birth, growth, transformation, and sometimes death, is being redrawn in real time as data accumulates. Galaxies are not static. They form from collapsing gas in dark matter halos, ignite with star formation, grow by merging with neighbours, and evolve through feedback processes that regulate gas supply. Some galaxies remain actively star-forming for billions of years. Others quench, ceasing star formation and settling into quiescence. Understanding why galaxies follow different evolutionary paths is a central question in astrophysics, and Webb provides unprecedented data to address it. The traditional picture, developed primarily from Hubble observations and ground-based surveys, describes a hierarchical assembly. Small proto-galaxies merge into larger structures, building up mass over cosmic time. Star formation peaks around redshift 2, roughly 10 billion years ago, when the universe was about 3 billion years old. Since then, the cosmic star formation rate has declined, and galaxies have grown more through mergers than through fresh star formation. This picture is broadly correct but coarse, lacking detail about the earliest epochs and the diversity of evolutionary pathways. Webb sharpens the picture by observing galaxies at redshifts above 6, corresponding to the first billion years. These observations reveal surprisingly mature structures, disk galaxies, spiral arms, bars, at epochs when such organization was not expected. The presence of morphological features implies that galaxies assembled and stabilized faster than simulations predicted, echoing the impossibly early galaxy theme discussed earlier. Theorists are revising models to account for this rapid organization, exploring whether early dark matter halos were denser, gas flows more efficient, or feedback weaker than assumed. Webb also observes quenching in action. Some high redshift galaxies show spectra indicative of old stellar populations, implying that star formation ceased billions of years ago. These quiescent galaxies at early times challenge models because quenching typically requires mechanisms: supernova feedback, black hole jets, environmental stripping that take time to develop. Finding quiescent galaxies at redshift 5 or 6 suggests that quenching began earlier and more efficiently than expected. Another puzzle for the theorists. Mergers are visible in Webb's images as interacting pairs and disturbed morphologies. The gravitational tides of a close encounter stretch galaxies into tidal tails, trigger starbursts and funnel gas towards central black holes. Webb's resolution distinguishes merging components that Hubble blurred into single sources, providing cleaner statistics on merger rates across cosmic time. These statistics inform simulations that trace galaxy evolution from the early universe to the present. There is a quirky observation worth noting. Some Webb images reveal galaxies with unusual colours or morphologies that do not fit standard categories: green pea galaxies, little red dots, and other whimsically named objects. These oddballs may represent transitional phases, evolutionary dead ends, or entirely new categories. Cataloguing and characterizing them is ongoing, and their significance may only become clear as the sample grows. Science often advances by paying attention to outliers, and Webb surveys are generating plenty. Historians of galaxy evolution recall that the very concept of galaxy is relatively recent. Until the 1920s, many astronomers believed the Milky Way was the entire universe, with spiral nebulae being internal features. Hubble's resolution of individual stars in Andromeda settled the debate, establishing that galaxies are island universes scattered across vast distances. Since then, galaxy evolution has grown into a major subfield, with generations of telescopes, Palomar, Hubble, Keck, Subaru, contributing data. Webb represents the latest generation, pushing observations to earlier epochs and finer detail than predecessors could achieve. The practical output of galaxy evolution studies is a kind of cosmic genealogy. By tracing how galaxies formed and changed, astronomers reconstruct the history of the universe's visible matter. That history includes the Milky Way, which assembled from smaller predecessors over billions of years, accreting gas and merging with dwarf galaxies that left stellar streams as fossils of past encounters. Understanding this history provides context for Earth's place in the cosmos, a small planet in a spiral galaxy that itself has a biography stretching back to near the Big Bang. Tonight, let the life cycle of galaxies flow through your thoughts. Birth in collapsing halos, growth through star formation and mergers, maturity in settled structures, quiescence when the fuel runs out. Webb captures galaxies at every stage, assembling a photo album that spans billions of years. You're part of one such galaxy, the Milky Way, and your existence depends on the processes Webb observes in distant cousins. Rest with that connection, and let the slow rhythm of galactic evolution ease you towards sleep. You approach now the edges of Webb's capabilities and glimpse the telescopes yet to come, instruments that will extend the vision Webb has opened and address questions it cannot fully answer. Science builds on itself, each generation standing on the shoulders of the previous, and Webb is both a culmination and a foundation. Webb excels in the infrared, from 0.6 to 28 microns, but this range has limits. Wavelengths shorter than 0.6 microns, ultraviolet and blue visible light, fall outside its sensitivity, requiring other instruments. Wavelengths longer than 28 microns, far infrared and submillimeter, are also beyond reach. For some science cases, these gaps matter. Observing the hottest stars, probing certain molecular transitions, and mapping cold dust require capabilities Webb lacks. Webb's mirror, though large for a space telescope, is not large enough to resolve certain fine details on exoplanets or distant galaxies. Direct imaging of Earth-like planets around Sun-like stars, for instance, requires both a large mirror and a coronagraph capable of blocking starlight to extreme levels. Webb has coronagraphic modes, but they are optimized for larger, brighter planets, not Earth analogues. Detecting biosignatures on truly Earth-like worlds will require future missions designed specifically for that task. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will complement Webb with a wide-field infrared camera capable of surveying large swathes of sky. Roman will map dark matter through weak lensing, discover thousands of exoplanets via microlensing, and measure cosmic expansion with Type Ia supernovae. Its field of view is 200 times larger than Webb's, enabling surveys that would take Webb centuries to complete. Roman is not a replacement but a partner, and the two telescopes will operate simultaneously for at least part of their missions. Looking further ahead, NASA is studying concepts for a habitable worlds observatory, a large space telescope designed specifically to image Earth-like planets and characterize their atmospheres. Such a mission would require a mirror larger than Webb's and coronagraphic technology beyond current capabilities. Development will take decades, but the scientific case is compelling, and Webb's discoveries are strengthening that case by identifying target systems and refining models. Ground-based telescopes also contribute. The extremely large telescope currently under construction in Chile will have a 39-meter mirror, dwarfing any space telescope. Adaptive optics will partially correct atmospheric distortion, enabling sharp infrared images for certain observations. Ground-based facilities excel at spectroscopy of bright targets and rapid follow-up of transient events. They cannot match Webb's sensitivity to faint, high redshift sources, but they complement space-based observations in important ways. There is a historical pattern worth noting. Each major telescope, Mount Wilson's 100-inch, Palomar's 200-inch, Hubble, now Webb, has revealed unexpected phenomena that shaped subsequent missions. The universe consistently surprises observers, and surprises drive innovation. Webb's discoveries, impossibly early galaxies, unexplained expansion tensions, supermassive black holes appearing too soon, will likely inspire future missions designed to address these specific puzzles. The cycle of observation, surprise, and response continues. Historians of astronomy recognize that telescope development is as much a social and political endeavor as a technical one. Webb's budget overruns and delays required sustained advocacy from scientists, public outreach to maintain support, and managerial reforms to keep the project on track. Future missions will face similar challenges, competing for funding against other scientific priorities and societal needs. The astronomical community's ability to articulate the value of cosmic exploration, cultural, educational, inspirational, will determine how many successors Webb ultimately has. Webb itself will operate for years, possibly decades, depending on fuel consumption and instrument health. The mission was designed for a minimum of 5 years, with a goal of 10 or more. Lagrange point 2 is stable, reducing fuel needs for orbital maintenance, and early operations suggest consumables may last longer than projected. As Webb ages, its observations will become more targeted, focusing on high-priority science that only it can accomplish, while Roman and ground-based facilities handle broader surveys. Tonight, let the future telescopes shimmer at the horizon of your imagination. Mirrors under construction in mountain deserts, spacecraft being designed in engineering labs, scientists writing proposals for observations that will not occur for years. The quest to understand the cosmos is multi-generational, each telescope inheriting questions from predecessors and bequeathing new questions to successors. Webb has asked some of the biggest questions in its first years. Future instruments will pursue the answers. Rest with that forward momentum and let the continuity of exploration carry you gently towards sleep. You arrive at last at a place of reflection, where the data and discoveries of Webb resolve into something more personal, a sense of scale, a feeling of humility, and a whisper of wonder that accompanies the closing of this journey. The universe revealed by Webb is vast beyond comprehension, ancient beyond imagination, and strange beyond expectation. And yet here you are, contemplating it from a small planet orbiting an ordinary star in one of trillions of galaxies. Scale is not merely a number, it is an experience. When you look at Webb's deep field and realize that each smudge of light contains billions of stars, many with planets, the numbers become almost meaningless. The human mind evolved to track maybe 100 individuals in a social group, to estimate distances in terms of a day's walk, to measure time by seasons and generations. Cosmic scale breaks these intuitions, demanding a different kind of understanding. Not emotional, but intellectual. Not visceral, but conceptual. You cannot feel a billion light years the way you feel a mile, but you can know it. Hold it in your mind as an abstraction that nonetheless refers to something real. Humility follows from scale. Whatever achievements humans have accomplished, art, science, civilization, occupy a tiny corner of a vast cosmos that existed for billions of years before us and will continue for billions after. This realization can inspire despair or awe, depending on temperament and context. Tonight, let it inspire awe. The universe did not have to be comprehensible. It did not have to produce beings capable of building telescopes and decoding starlight. That it did is remarkable, a contingency worth celebrating. Webb has revealed that the universe is stranger than we thought. Galaxies formed faster, black holes grew larger, expansion rates disagree, and atmospheres of distant worlds contain molecules that hint at chemistry beyond Earth. Each surprise is an invitation to revise understanding, to admit ignorance, and to pursue knowledge with renewed vigor. Science thrives on surprises. Complacency is the enemy of discovery. Webb has banished complacency for a generation of astronomers. There's also beauty in Webb's images, a beauty that transcends scientific content. The colours may be false, the scales incomprehensible, but the aesthetic impact is immediate. Nebulae glow like stained glass. Galaxies spiral like hurricanes frozen in time. Stars punctuate the dark like scattered diamonds. You do not need to understand astrophysics to appreciate these images. They speak a visual language that bypasses analysis and reaches something deeper. Art and science converge in Webb's data releases, and millions of people who will never read a journal article have nonetheless been moved by what the telescope has shown. Philosophers have long debated the significance of cosmic scale for human meaning. Some argue that a vast, indifferent universe renders human concerns trivial. Others contend that meaning is created by conscious beings regardless of external context, and that cosmic scale is irrelevant to personal significance. Still others find a middle path, suggesting that awareness of the cosmos enriches meaning by connecting individual lives to a larger story. Tonight, adopt whichever perspective brings comfort. The universe offers no prescriptions, only data. Interpretation is yours to make. Webb's mission is, in one sense, an act of profound optimism. Humans invested billions of dollars and decades of effort to build a telescope that would answer questions about the universe's origins and composition, questions with no immediate practical application, no economic return, no military advantage. The investment reflected a belief that knowledge is valuable for its own sake, that understanding where we came from and what surrounds us is worth pursuing, even if the answers change nothing about daily life. That belief is not universal, but it is widespread enough to have launched Webb into space, and to have cheered when its images arrived. You have travelled far tonight, from the golden mirror unfurling at Lagrange point 2 to the earliest galaxies that defy expectations, from redshift and the expanding universe to the tension between measurements that refuse to agree, from supermassive black holes that grew too fast to dark matter that shapes everything unseen, from stellar nurseries glowing in infrared to exoplanet atmospheres tasted for the first time, from the search for biosignatures to the cosmic chemistry that built your atoms, from galaxy evolution rewritten in real time to the telescopes yet to come. Each section has added a layer to your understanding, a thread to the tapestry of cosmic knowledge. Now, as the journey ends, let the tapestry wrap around you like a blanket. The universe is vast, but you are part of it, made of its material, shaped by its processes, aware of its existence. Webb's photons have travelled billions of years to reach detectors that convert them into images and spectra, which are then translated into words and stories, which are now settling into your mind as you drift towards sleep. The chain of causation is unbroken, from ancient starlight to present consciousness. So close your eyes, let the images fade into soft impressions, let the numbers dissolve into feelings, let the questions remain unanswered for now. They will still be there tomorrow, tended by scientists who wake while you dream. The universe does not require your attention to continue, but your attention enriches the universe, adding a node of awareness to the vast network of existence. Rest well, knowing that the cosmos holds you gently, indifferent but sustaining, immense but intimate in the sense that you are made of its substance and participate in its unfolding. The light will still be falling when you wake, ancient photons arriving on schedule, carrying news from epochs before memory. Webb will still be watching, golden mirrors cold in the vacuum, instruments humming with data. And you will still be here, breathing air made of atoms forged in stars, dreaming dreams made possible by a cosmos that somehow produced dreamers. Until then, let the silence of space become the silence of sleep. The universe has told you its story tonight. Now rest, and let the stars keep vigil until morning. Sweet dreams.